Please subscribe to the channel to support the channel. Somewhere out in the night sky, tucked away in the graceful wings of the constellation Cygnus, lies a star that has challenged everything we thought we knew about how stars behave. This is no ordinary star. It does not shine in a predictable rhythm, nor does it dim in a way that astronomers can easily explain. This star, known officially as KIC 8462852, but more famously as Tabby's star, has puzzled scientists, captivated the public, and inspired countless theories ranging from dust clouds to alien megastructures. It's been called the most mysterious star we've ever discovered, and its story is a fascinating mix of science, curiosity, and imagination. To begin unraveling this mystery, let us start with the introduction to why Tabby's star stands apart from all the billions of stars we see across the cosmos. When astronomers study stars, especially with missions like Kepler, they expect to see patterns. Stars can flicker due to stellar activity, sunspots, or orbiting planets passing in front of them. But Tabby's star immediately stood out because it didn't just flicker, it dipped in brightness in ways that made no sense according to any astrophysical model known at the time. Imagine a lighthouse beam that suddenly dims to almost a quarter of its light output and then recovers unpredictably, only to fade again at odd intervals. That is the kind of strange and irregular behavior that drew the world's attention to this enigmatic star. This mystery is not just about one star behaving oddly, it's about how its behavior completely defies expectations. For centuries, humanity has looked at the stars and mapped out patterns, laws, and cycles. We've learned how planets orbit, how stars are born and die, and how galaxies evolve. But Tabby's star threw a wrench into all of that certainty. Its strange dimming patterns were too deep to be explained by orbiting planets, too irregular to be the simple cycle of a variable star, and too long-lasting to be a random fluke. This meant that something truly unusual was happening, and for astronomers, that was both frustrating and exhilarating. What makes this mystery so compelling is that it opened the door to ideas far beyond the ordinary. At first, the dimming seemed so extreme that some scientists half-seriously suggested it might even be caused by alien technology, an idea that spread rapidly across the media and captured imaginations worldwide. While scientists remain cautious and skeptical of such extraordinary claims, the very fact that the possibility was even mentioned shows how unprecedented this star's behavior was. So when we introduce the story of Tabby's star, we're not just introducing a single strange object in space, we're diving into a cosmic puzzle that challenged astronomers to question what they thought they knew, to revisit data with fresh eyes, and to involve not only professionals but also citizen scientists in unraveling the clues. It's a story that bridges hard science with human wonder, skepticism with imagination, and it remains one of the best modern examples of how mysterious the universe can be. Tabby's star, this beacon of mystery that has captivated astronomers and dreamers alike, is not hiding in some distant, unreachable corner of the universe. Instead, it resides in a place that many amateur stargazers are already familiar with, the beautiful constellation Cygnus, also known as the Swan. This constellation dominates the northern summer sky, flying gracefully along the dense star fields of the Milky Way. If you've ever looked up during a clear summer night and seen the bright cross-shaped pattern often called a northern cross, you've seen Cygnus. And nestled among its wings, about 1,470 light-years away, is where Tabby's star resides. Now, let's pause and really appreciate what 1,470 light-years means. 1 light-year is the distance light travels in a single year, nearly 6 trillion miles, or about 9.5 trillion kilometers. That means Tabby's star is not just a little down the cosmic road, it's staggeringly far. The light we see from it tonight, whether through telescopes or captured by instruments like Kepler, began its journey long before humans built the pyramids, long before recorded history, even before many civilizations existed. Around the time the Anglo-Saxons were first arriving in Britain, photons of light from Tabby's star were leaving its surface, racing across the vacuum of space, and only now, over 1,000 years later, they finally enter our telescopes. In a way, when we look at Tabby's star, we're gazing back in time. Cygnus itself is a fascinating neighborhood in the night sky. It is full of notable stars and deep sky objects. The constellation contains Deneb, one of the brightest stars in the sky and part of the famous Summer Triangle. It also houses the North America Nebula, the Veil Nebula, and countless star-forming regions along the Milky Way's dense band. To think that Tabby's star is located among all this cosmic beauty gives it a kind of poetic resonance. In a constellation named after a swan, graceful and serene, lies a star that defies serenity and instead shrouds itself in mystery. But what about the star itself? Tabby star is an F-type main sequence star, which means it's slightly larger, hotter, and brighter than our own Sunday. It is not unusual in its classification. By all accounts, it should behave like a normal stable star, shining consistently, without massive unpredictable fluctuations in brightness. If we were to simply look at its spectral type and its basic properties, there would be no reason to suspect it would become the most mysterious star ever studied. That's what makes its location and identity so striking. It is just one of many stars in Cygnus, indistinguishable to the naked eye, and yet it harbors a secret that has baffled some of the best minds in astronomy. If you were to step outside on a dark night with minimal light pollution, you wouldn't be able to see Tabby's star with your unaided eyes. It's far too dim, at magnitude 11.7. For comparison, the faintest stars visible to the naked eye under ideal conditions are around magnitude 6. So you'd need a decent telescope to even catch a glimpse. But with that telescope, if you trace your way through Cygnus, past the bright wings of Deneb and across the Milky Way's river of stars, you could find the small, unassuming point of light that is Tabby's star. It doesn't stand out visually. You wouldn't suspect it was hiding a story more strange than science fiction. But appearances can be deceiving, especially in astronomy, and that dim point of light is the source of one of the greatest cosmic puzzles of the 21st century. The location in Cygnus is also significant because it fell directly within the field of view of NASA's Kepler Space Telescope, which is why it was noticed in the first place. Kepler was designed to stare at a fixed patch of sky in Cygnus and Lyra, monitoring the brightness of over 150,000 stars continuously for years on end. This was the perfect hunting ground for planets, because when a planet passes in front of its star, it causes a tiny but measurable dip in brightness. Cygnus, rich in stars, provided Kepler with a goldmine of opportunities. And among all those thousands upon thousands of stars, Tabby's star stood out like an anomaly, a piece of data that refused to fit the neat patterns astronomers were used to. Another reason the star's distance and position matter is that they add layers to the mystery. At 1,470 light-years, it's too far away for us to simply go and check. Unlike nearby stars that we can study in high detail, Tabby's star sits in that frustrating middle ground, far enough away that fine details are blurred, but close. Enough that we can detect its peculiarities through careful observation. This distance keeps the mystery alive, because every photon of data we receive is precious, and interpreting it requires caution, patience, and creativity. The fact that Tabby's star is in Cygnus also helps with public engagement. Cygnus is visible in much of the world, and many amateur astronomers feel a special connection to it. When the story of Tabby's star broke into mainstream news, people could step outside, point to the Northern Cross, and know that somewhere in that region was the most bizarre star humanity had ever found. This tangibility, the ability to connect a wild scientific mystery to a spot in the sky people can see themselves, was a big part of why it captured so much attention. In summary, Tabby's star is located in Cygnus, about 1,470 light-years away. It's an ordinary-looking F-type star in an extraordinary situation, hiding within one of the most visually rich and accessible parts of the sky. Its location made it a prime target for Kepler's long-term monitoring, which is how the mystery began. And perhaps most importantly, its position within such a familiar constellation gave the public a cosmic anchor, a place they could look up to and imagine the puzzle that even the best astronomers have yet to fully solve. Somewhere in the early 2000s, long before the mystery of Tabby's star would make headlines and ignite imaginations, a spacecraft was being designed with a simple but revolutionary mission: to find other worlds. This spacecraft was NASA's Kepler Space Telescope, and its goal was to answer one of humanity's oldest questions. Are we alone, or do planets like ours orbit other stars across the galaxy? To do this, Kepler would spend years staring at one small patch of the sky, tracking the tiniest dips in starlight that might betray the presence of orbiting planets. It was within this very patch of the sky, rich with stars in the constellations of Cygnus and Lyra, that Kepler's unblinking eye fell on Tabby's star. The idea behind Kepler was deceptively straightforward. If a planet passes in front of its star as seen from Earth, the star's light dims slightly, much like a moth flying across a lamp. Astronomers call this a transit, and with enough precision, you can measure these dips in brightness to infer not only the presence of a planet but also its size, orbit, and even, in some cases, its atmosphere. This technique is known as the transit method, and it has become one of the most powerful tools in the hunt for exoplanets. Kepler was designed with a camera capable of detecting brightness changes as small as 0.01%, a level of precision that would allow it to spot Earth-sized planets orbiting Sun-like stars hundreds or even thousands of light-years away. To achieve this, Kepler stared at the same patch of sky continuously from 2009 until its mission was hindered by mechanical failures in 2013, and even then, it continued in a modified mission called K2. During those years, Kepler monitored over 150,000 stars in Cygnus and Lyra, collecting mountains of data and revolutionizing exoplanet science. Before Kepler, astronomers knew of a few hundred exoplanets. Thanks to Kepler, that number exploded into the thousands, completely transforming our understanding of how common planets are in the universe. And yet, among all of those stars, Tabby's star was unlike anything else Kepler saw. Most of the time, Kepler's data showed neat, repeating patterns of dimming, signatures of planets that passed in front of their stars in regular orbits. But when Kepler observed Tabby's star, it recorded dips that were neither small nor periodic. They were vast, sometimes blocking up to 22% of the star's light, and they occurred in unpredictable, chaotic ways. This was not the simple shadow of a planet moving in a clockwork orbit. This was something far stranger. The reason Kepler even noticed Tabby's star at all was because it was in its line of sight. The telescope had chosen Cygnus and Lyra partly because these regions sit along the plane of the Milky Way, where stars are densely packed. That density maximized Kepler's chances of spotting transiting planets. But within that density also lurked anomalies, rare events that had nothing to do with planets, but everything to do with the unpredictable drama of the cosmos. Tabby's star was one such anomaly, hiding in plain sight until Kepler's patient eye revealed its strangeness. Kepler's mission was not built to chase mysteries like this. It was built to find planets, to catalog them, to build statistics about how common Earth-sized worlds might be. And yet, its sheer volume of data made it inevitable that astronomers would stumble upon something unexpected. That's the beauty of big science projects. You set out with one purpose, but the sheer scale of data ensures that surprises will emerge. Tabby's star is one of the most dramatic examples of this. It wasn't a planet that Kepler found around this star. Instead, it found a puzzle so perplexing that it would ripple far beyond the scientific community and into mainstream culture. Kepler's role in all of this cannot be overstated. Without Kepler's relentless precision and long-term monitoring, Tabby's star would have remained just another unremarkable F-type star, lost among the billions in our galaxy. Ground-based telescopes would never have noticed its subtle but dramatic dimming, because Earth's atmosphere makes it difficult to monitor a single star continuously with the accuracy Kepler provided. Only by staring at the same patch of sky, uninterrupted for years, could Kepler accumulate the kind of data that revealed the bizarre fluctuations of Tabby's star. It's also worth noting the emotional aspect of Kepler's discoveries. When the telescope launched in 2009, there was excitement, yes, but also uncertainty. Could it really detect Earth-like planets? Could it live up to the grand expectations of discovering new worlds? Kepler not only delivered on those promises but gave us something we didn't even know to ask for, mysteries like Tabby's star. In a sense, the star is a gift of serendipity, an unexpected outcome of a mission that was already groundbreaking in its success. And this is where the threads of our story begin to weave together. We began with the introduction of a star unlike any other, a star that defied astrophysical explanations. We then located it in the constellation Cygnus, a swan-shaped beacon soaring along the Milky Way, about 1,470 light-years away. And now, with Kepler's mission, we understand how and why this star came under scrutiny in the first place. It was not targeted for its mystery, but rather swept up in Kepler's vast survey of stars. Yet from that survey, it emerged as the strangest of them all, a cosmic outlier that demanded attention. In hindsight, this was almost inevitable. When you collect data on 150,000 stars, you're bound to stumble across oddities. Just as if you sifted through a million grains of sand, you might find one glittering fragment that isn't sand at all. Tabby's star was that glittering fragment, the anomaly hiding among thousands of normal light curves. It's a reminder that in science, the unexpected often becomes the most valuable discovery of all. When the Kepler Space Telescope was launched, astronomers had a very clear expectation of what they were supposed to see when they looked for planets. A planetary transit, in its simplest form, is one of the cleanest, most predictable signals in all of astronomy. Imagine watching a star through Kepler's sensitive eye. The star shines steadily, its light constant, until something small and dark drifts across its face. That something, if it repeats in a steady rhythm, is almost certainly a planet. A normal transit curve looks like a gentle U-shaped dip in brightness on a graph. The light drops as the planet begins to cross the star, called ingress, levels out slightly as the planet blocks a consistent fraction of light during its full passage, the transit itself, and then rises back to normal brightness as the planet moves off the star's face, egress. These dips are small, often less than 1% of the star's total brightness for giant planets and much less for Earth-sized ones. But the beauty of transits lies in their regularity. If you observe a dip every, say, 365 days, you know you're likely looking at a planet in a yearly orbit. That repeating pattern tells astronomers the orbital period, the size of the planet, and even gives clues about whether it might be in the habitable zone of its star. Kepler was exquisitely good at detecting these normal transits. Most of the stars it monitored showed either no variation or predictable patterns consistent with planetary systems. That's why astronomers could build catalogues of thousands of exoplanets with confidence. The process was almost algorithmic. Find dips, check if they repeat, measure them, confirm with follow-up observations. But Tabby's star? Tabby's star refused to play by these rules. When Kepler recorded its light curve, what it saw was not the smooth, periodic dips of planets. Instead, the dips were jagged, irregular, and extreme. Instead of a clean U-shape dipping by less than 1%, Kepler saw sudden plunges of brightness that sometimes reached 22%. That's catastrophic by transit standards. To put that into perspective, if Jupiter, the largest planet in our solar system, passed directly in front of the Sun as viewed from Earth, it would only block about 1% of the Sun's light. For Tabby's star to dim by over 20%, whatever was blocking the light would need to be massive, far larger than any planet. And yet, unlike a planet, these dips didn't repeat in any regular fashion. They seemed to come out of nowhere, with no obvious rhythm or cycle. To astronomers trained to recognize the clean geometry of planetary transits, Tabby's star looked like chaos. One dip might last just a few days, another might stretch on for weeks. Some were shallow, others were incredibly deep. The timings were inconsistent, the shapes varied, and nothing about the pattern resembled the orderly ticking of an orbiting planet. It was like listening to a piece of music where the notes were random, discordant, and unpredictable, when you were expecting a steady, repeating melody. This stark contrast between the predictable and the anomalous is what first flagged Tabby's star as something extraordinary. If the dips had been shallow and repeating, astronomers might have logged it as another planetary system and moved on. If they had been deep but regular, perhaps a massive object or multiple planets could explain it. But the combination of depth, irregularity, and unpredictability placed it outside any familiar category. It was as though Kepler had stumbled upon a language written in an alphabet no one had ever seen before. The anomaly of Tabby's star was not just about the data, it was about the expectations that data defied. Kepler's entire mission was built on the premise that stars are steady, reliable lanterns whose light only dims in neat, measurable ways when planets cross them. Tabby's star shattered that assumption, showing that sometimes, a star doesn't follow the script. This is a crucial turning point in the narrative. The mystery wasn't just that Tabby's star dimmed, but that it dimmed in ways that broke every rule astronomers thought they understood about transit behavior. And so, the comparison is clear. Normal. Planetary transits are like clockwork, small, predictable, periodic. Anomalies like Tabby's star's light curve are erratic, deep, and baffling. To make sense of it, astronomers had to abandon the comfortable models of planetary systems and entertain the possibility of something entirely new. The true heart of the Tabby star mystery lies in its irregular dimming, a behavior so extreme and so unpredictable that it immediately set this star apart from every other one Kepler was monitoring. To understand just how unusual this is, we need to look closely at the numbers and patterns. When Kepler was observing the star, it recorded sudden dips in brightness, sometimes small, sometimes colossal. These dips could last for days or even weeks, and then, just as mysteriously, the star's brightness would return to normal. The most shocking event was a dimming of nearly 22% of the star's total light. That figure alone is staggering. As mentioned earlier, even if Jupiter, the largest planet in our solar system, were to pass in front of the Sun, it would block only about 1%. For Tabby's star to drop by over 20%, whatever was causing the dimming would have to be massive, something far larger than a planet. But size wasn't the only problem. The real kicker was irregularity. Planetary transits repeat on a schedule. They're like clockwork. Every few days, months, or years, the same dip in brightness returns as the planet goes around its star. Tabby's star didn't follow that rhythm. Its dips appeared randomly, without any periodicity. Sometimes the star dimmed drastically, other times only slightly. Some dips were sharp and sudden, while others were gradual, like a curtain slowly being drawn across the star. There was no order, no predictability, only chaos. Astronomers refer to the star's light curve, the graph of brightness over time, as one of the strangest they've ever seen. Normally, a light curve is smooth and repetitive. With Tabby's star, it looked like a jagged, unpredictable landscape, with deep valleys scattered seemingly at random. There was no clear orbital period to latch onto, no symmetry, no regularity. It was as if something enormous, irregularly shaped, and inconsistent was drifting in front of the star, but not in any way that fit existing models. The depth and irregularity of the dimming meant that planets were immediately ruled out as an explanation. Not only were the dips too deep for planets, but their irregular nature made orbital motion an impossible explanation. Even multiple planets couldn't produce such chaotic results, since planetary orbits are still predictable. Something else had to be happening. And the more astronomers studied the data, the more confusing it became. Between 2009 and 2013, Kepler observed Tabby's star dimming multiple times, with varying depths. Some events lasted just a few days, others stretched to almost 100 days. No other star in Kepler's field showed anything like this. Out of 150,000 stars monitored, only Tabby's star displayed this bizarre behavior. That fact alone made it extraordinary. Adding to the puzzle was the long-term dimming trend. Later studies using old photographic plates suggested that Tabby's star had been gradually dimming over the course of a century, something stars simply aren't supposed to do at this stage of their lives. This slow fading, combined with the sudden deep dips, created a double-layered mystery. Not only was the star behaving erratically in the short term, but its long-term brightness history also defied expectations. For astronomers, this was both thrilling and maddening. On one hand, it was clear that Tabby's star was doing something unique, something that could potentially expand our understanding of stellar behavior or cosmic structures. On the other hand, the data didn't match any known category. Dust. Too extreme. Planets. Impossible. Stellar variability. Not consistent with an F-type star like this. It was the perfect recipe for scientific curiosity, because when the universe throws a curveball like this, scientists are forced to stretch their imagination and test the limits of what's possible. The irregular dimming became the defining feature of Tabby's star. This was the hook that pulled in both professional astronomers and the general public. The numbers, 22%, irregular, unpredictable, were repeated in headlines, podcasts, and documentaries. It was the kind of astronomical anomaly that demanded an explanation but resisted every obvious one. And that resistance is what made the story so compelling. In astronomy, when something can't be explained by the usual suspects, planets, dust, or stellar activity, it opens the door to speculation. And in the case of Tabby's star, speculation would soon lead to one of the most attention-grabbing ideas of all time. Could it be an alien megastructure? But before that hypothesis gained traction, there was a period of sheer bewilderment. Astronomers were faced with data that didn't fit any model they had. They had to admit, quite openly, that they were baffled. And in science, that is both a moment of humility and of opportunity. When the data from Kepler first revealed the bizarre behavior of Tabby's star, the reaction among astronomers was one of genuine confusion. And that is not a word scientists use lightly. In astronomy, even the strangest phenomena usually have at least a plausible explanation. Supernovae explode spectacularly, but we understand the physics behind them. Stars pulsate or flare, but their variability follows well-established categories. Even when something is rare, it usually fits somewhere within the frameworks astrophysics has built over decades. But Tabby's star? It fit nowhere. The first wave of researchers who examined the light curves were stunned. Here was a star that looked normal in every other respect, It was a stable F-type star, slightly larger and hotter than the Sun, and not at a stage in its life where massive fluctuations should occur. Yet its light curve looked like nothing ever seen before, deep, erratic dips of brightness with no pattern, no symmetry, and no precedent. It was, in a word, baffling. Astronomers began by running through the usual suspects. Could it be planets? No, planets, even giant ones, simply don't block 22% of a star's light. Could it be stellar variability? That didn't fit either, because stars like Tabby's don't behave that way. F-type stars are stable, and while they can have star spots or slight fluctuations, they don't plunge in brightness unpredictably. Could it be instrument error? That was checked and rechecked, but the data was solid. Kepler was designed to measure brightness with extreme precision, and no other stars in the same field of view showed similar issues. The anomaly was real. One of the earliest theories involved clouds of comets. Perhaps a giant swarm of comets, breaking apart or clustering together, was drifting in front of the star and blocking its light in irregular ways. This had some appeal. It could explain irregular dimming events, since comets can be erratic. But even this idea strained credibility. To cause a 22% drop, you would need an almost unimaginably large swarm of comets, coordinated in a way that seemed implausible. Astronomers often say that while comets are messy, they're not that messy. Another thought was that maybe we were seeing the debris from some catastrophic collision. Perhaps two planets had smashed into each other, producing a chaotic cloud of dust and rubble that temporarily dimmed the star. But again, problems arose. Such debris would radiate heat in the infrared spectrum, and when astronomers checked, Tabby's star didn't show the infrared glow you'd expect from a massive debris field. That meant no giant cloud of warm dust, no recent catastrophic collision. Even more exotic natural explanations, such as some form of intrinsic stellar variability unique to Tabby's star, didn't match. Stars do pulsate and fluctuate in brightness, but never in such dramatic and asymmetric ways. It was as though the star itself had signed out of the rulebook of stellar physics. This confusion was profound enough that, for the first time in decades, astronomers found themselves entertaining ideas far outside the norm. It wasn't that they were ready to declare aliens the answer, but the fact that the word even entered the discussion tells you how far outside ordinary astrophysics this case was. The early period of studying Tabby's star was filled with paper after paper proposing hypotheses, each one hitting a wall of contradictions. Dust. It didn't quite fit. Comets. Too far-fetched. Planetary debris. No infrared glow. Stellar variability. Not like this. The scientific process thrives on this kind of confusion, but it can also be frustrating. In astronomy, when something doesn't make sense, you usually gather more data, refine your models, and eventually the pieces fall into place. With Tabby's star, the more data astronomers looked at, the stranger it became. Historical photographic plates showed long-term dimming over decades, which added yet another layer to the mystery. Short-term dips and long-term fading didn't fit neatly into a single explanation. The star was unusual in multiple ways, compounding the confusion. For many astronomers, this was both exhilarating and humbling. On the one hand, this was a mystery that promised the potential for a breakthrough, an entirely new kind of astrophysical phenomenon waiting to be discovered. On the other hand, it highlighted how limited our understanding could be. Tabby's star was a reminder that even with our powerful telescopes and sophisticated models, the universe could still throw us puzzles that left us scratching our heads. The bafflement surrounding the star also created a unique situation. It invited not just professionals but also citizen scientists into the fold. Since Kepler produced such enormous amounts of data, volunteers were enlisted to help scan light curves for anomalies. And it was these volunteers who first flagged Tabby's star as unusual, marking the beginning of its rise to global fame. But before we get to their role, it's important to appreciate this moment of initial confusion. Scientists, trained to categorize and explain, were confronted with a phenomenon that resisted categorization. The early papers about Tabby's star read like a checklist of eliminated possibilities, a forensic process of narrowing down what it could not be. And with every ordinary explanation that failed, the star's reputation as the most mysterious star we've ever discovered grew stronger. Somewhere in the middle of Kepler's enormous ocean of data, there was a light curve unlike any other, a jagged, chaotic pattern that didn't belong to planets, stars, or any known cosmic event. What's remarkable is that it wasn't a seasoned astronomer at NASA who first pointed to this curve and said, "Wait a second, this is strange." Instead, it was citizen scientists, ordinary people with no professional training in astrophysics, who first recognized the anomaly that would one day be called Tabby's star. To understand their role, we need to talk about a project called Planet Hunters. When the Kepler mission began producing torrents of data, astronomers quickly realized that the sheer scale was overwhelming. Kepler was observing over 150,000 stars at once, each with years of continuous brightness data. Automated algorithms were excellent at spotting neat, repeating dips, the kind produced by planets, but they often missed subtler or irregular patterns. That's where human eyes came in. Planet Hunters was born as part of the Zooniverse platform, a collection of citizen science projects that allow volunteers around the world to help analyze scientific data. Anyone with an internet connection could log on, look at Kepler's light curves, and flag anything that looked unusual. The philosophy was simple but powerful. While computers are great at detecting specific patterns, humans excel at noticing the unexpected. And it was in this crowdsourced digital observatory that Tabby's star first caught attention. In 2011, volunteers scrolling through light curves noticed something that looked wrong. Instead of the gentle, periodic dips of a planet, they saw enormous, irregular plunges in brightness, something the algorithms had not flagged. The volunteers began discussing it in the Planet Hunters forum, comparing notes, expressing astonishment, and encouraging one another to look more closely. They didn't know exactly what they were seeing, but they knew it wasn't ordinary. Over time, their chatter began to converge. This star was weird. Really weird. This collective recognition by everyday people is extraordinary. Without Planet Hunters, Tabby's star might have sat unnoticed in the database, buried under tens of thousands of other light curves. The algorithms would have passed over it, discarding it as noise or an anomaly unfit for the mission's goal of detecting planets. Instead, because real human beings were given the opportunity to explore the data directly, the anomaly was brought to light. This is where the story takes on a deeply human dimension. Science is often portrayed as the domain of experts in ivory towers, but Tabby's star is a reminder that discovery can be a shared enterprise. The volunteers who flagged the star weren't astrophysicists. They were teachers, students, hobbyists, retirees, people who simply loved the idea of helping unravel the mysteries of the cosmos. And their curiosity was enough to change the course of the star's story. The Planet Hunters team eventually escalated the anomaly to professional astronomers, who realized this was worth serious attention. Among those who took notice was Tabitha Boyajian, an astronomer who would become the central figure in bringing Tabby's star to the scientific forefront. Boyajian, working with a group of collaborators, dug into the Kepler data and began to carefully analyze the bizarre light curves. The result was a landmark 2015 paper that formally introduced the world to K84628552, the star that would soon be nicknamed Tabby's star in her honor. But it's important to emphasize that without the volunteers, none of this might have happened. This wasn't just a case of citizen scientists supporting professional science in the background. This was a case of citizen scientists leading the way, being the first to raise the flag that said, "Look at this one, something's not right." They turned a hidden anomaly into a global scientific mystery. Their involvement also fueled the public fascination that would follow. Because the discovery was rooted in citizen science, the story carried a sense of accessibility. This wasn't just some distant academic paper. This was something ordinary people had been directly part of. It gave the mystery of Tabby's star a participatory feel, a sense that the whole world could play a role in solving it. It's no exaggeration to say that the citizen scientists of Planet Hunters changed the trajectory of exoplanet research by insisting this strange light curve deserved attention. They forced the question, what is happening around this star? And in doing so, they opened the door for the flood of hypotheses, debates, and speculations that would follow. When the mystery of KIC84628552 began to draw serious attention from the professional astronomical community, it needed something more memorable than a sterile catalog number. Numbers like KIC84628552 are useful for databases, but they don't spark curiosity in the public imagination. The star's story already involved passionate volunteers and an anomaly so bizarre that it felt like science fiction. What it needed was a human name, a symbol of the person who took this weird light curve and said, "This is worth the world's attention." That person was Tabitha Boyajian. Tabitha "Tabby" Boyajian was a postdoctoral researcher at Yale University when the Planet Hunters volunteers flagged the unusual data. She became fascinated by the star and quickly recognized that it wasn't just another blip in Kepler's vast dataset. It was a puzzle that demanded a deeper look. Working with colleagues, she led the effort to rigorously analyze the star's erratic dips and compile the evidence into a comprehensive scientific paper. In 2015, Boyajian published a landmark study, titled "Where's the Flux?", which laid out the case for just how strange Tabby's star really was. The title itself, witty, catchy, and slightly cheeky, hinted at the playful bafflement that scientists felt while grappling with the data. The paper carefully examined and dismissed many of the simplest explanations. It ruled out planets, questioned the plausibility of comets, and underscored the truly unprecedented nature of what Kepler had observed. It was this paper that formally introduced KIC 8462852 to the wider scientific world, transforming it from a curious anomaly in a citizen science forum to one of the most famous stars in astronomy. Because of Boyajian's central role in this process, the star soon acquired a nickname, Tabby's star. The nickname caught on quickly, first among colleagues and then in the broader scientific and public conversation. It served two purposes at once. It honored the astronomer who brought the star to prominence, and it gave the mystery a human face. After all, it's easier to talk about Tabby's star than KS 8462852. And in a sense, the nickname made the enigma more approachable, more relatable, and more memorable. For Boyajian, the naming was more than just a personal honor. It represented the collaborative nature of the discovery, a partnership between professional scientists, volunteers from Planet Hunters, and the Kepler mission itself. By carrying her name, the star's story became tied to the narrative of persistence, curiosity, and collaboration that defined its discovery. It wasn't just another anonymous point of light catalogued in a survey. It became a character in the unfolding drama of science, and Tabby was its advocate. The naming also had an important impact on public engagement. Astronomy thrives on storytelling, and Tabby's star immediately gave journalists, educators, and science communicators a compelling hook. The story of this mysterious, flickering star wasn't just about data. It was about Tabby, a scientist who looked at the universe and dared to say, "Something's not adding up here." Her leadership and openness to exploring even the strangest possibilities turned the star into an international sensation. Tabby Boyajian herself embraced the public's interest in the mystery. She worked tirelessly not just on the scientific side but also on outreach, engaging with podcasts, documentaries, and public talks. She also spearheaded a Kickstarter campaign to fund continued observations of the star after Kepler's mission ended. Thousands of ordinary people contributed, raising over $100,000 to allow professional telescopes to keep watching Tabby's star from Earth. This was another unprecedented moment in astronomy, the general public directly funding a long-term monitoring project of a single star, all because its mystery was too compelling to ignore. The name Tabby's star, then, is more than just a convenient nickname. It's a reminder of how discoveries in modern science often happen, through collaboration between professional expertise and public curiosity, through perseverance in the face of confusion, and through the leadership of individuals who take strange data seriously. Boyajian's role was pivotal. Without her, the star might never have moved from an oddity in a citizen science forum to a central topic of modern astrophysics. It's also a testament to how science progresses. Not with lone geniuses making sudden discoveries in isolation, but with communities, volunteers, scientists, telescopes, institutions, all converging around a puzzle. Tabby's name became the thread that tied together those communities, giving the star's mystery a personal identity. And so, KIC 8462852 became Tabby's star, a name that feels less like a sterile catalogue entry and more like the title of a legend. A name that evokes both the scientist who brought it to light and the deep mystery that still surrounds it. When the mystery of Tabby's star began to spread beyond the astronomy community and into the public imagination, one idea stood out above all the rest. An idea so audacious, so provocative, that it instantly transformed the star from an obscure astrophysical puzzle into a cultural phenomenon. That idea was this: maybe the irregular dimming of Tabby's star wasn't caused by dust or comets at all. Maybe, just maybe, it was evidence of an alien megastructure. Now, before we dive into what that means, it's important to understand why the thought even entered the conversation. Scientists are by nature cautious, skeptical, and grounded in natural explanations. But Tabby's star's light curve was so unusual that it seemed to resist every simple theory. Planets couldn't explain it. Stellar activity didn't fit. Collisions and debris didn't produce the expected infrared signatures. Each hypothesis either fell short or raised more questions than it answered. In such a vacuum of explanation, the mind inevitably drifts to more radical possibilities. The alien megastructure idea was first publicly suggested by Jason Wright, an astronomer at Penn State University. In 2015, Wright and colleagues proposed that perhaps the star's bizarre dimming could be the result of something artificial: vast structures constructed by an advanced civilization orbiting the star. The idea drew from a concept first put forward by physicist Freeman Dyson in 1960, now known as the Dyson sphere. A Dyson sphere isn't necessarily a literal solid shell around a star that would be impossible with current physics, but rather a swarm of satellites, panels, or structures designed to capture a star's energy. The logic is simple: as civilizations advance, their energy needs grow. Eventually, they may harness not just their planet's resources, but their entire star's output. A Dyson-like structure would harvest enormous amounts of energy, but from afar, it could also block and scatter starlight in irregular ways. And that, Wright argued, might just look like what Kepler saw with Tabby's star. This suggestion electrified the media. Headlines proclaimed the possibility of an alien megastructure around a distant star. Documentaries, podcasts, and late-night shows seized on the story. People around the world suddenly knew about Tabby's star, not because of dust or comet hypotheses, but because of the tantalizing whisper, "What if it's aliens?" For a brief moment, the mystery wasn't just a scientific curiosity, it was a cultural event. It's important to stress that Wright and other astronomers weren't claiming aliens were the explanation. Rather, they were being scientifically honest. Tabby's star's behavior was so strange that it was worth considering all possibilities, however unlikely. As Carl Sagan once famously said, "Extraordinary claims require extraordinary evidence." No one was ready to declare that aliens had been found, but the fact that such a possibility couldn't be immediately dismissed was enough to fuel endless speculation. The Dyson sphere idea also resonated because it played directly into human imagination. Science fiction has long explored the idea of advanced civilizations building vast cosmic structures, ringworlds, star-encompassing habitats, or energy-harvesting megastructures. To think that Kepler might have accidentally stumbled across real evidence of such a thing was thrilling, even if improbable. It bridged the gap between astrophysics and the dream of contact with intelligence beyond Earth. And for the general public, it was irresistible. Here was a star with dips too deep for planets, too irregular for known stellar behavior, too puzzling for easy answers. Combine that with a concept as evocative as a Dyson sphere, and you had the perfect recipe for fascination. Tabby's star became the alien megastructure star in popular conversation, a mystery that seemed to dangle the possibility of proof that we are not alone in the universe. Of course, scientists approached the idea with caution. The vast majority of astronomers emphasized that natural explanations, however convoluted, were far more likely than artificial ones. But at the same time, no one could deny how captivating the possibility was. Even the faintest suggestion that we might have glimpsed the engineering of another civilization was enough to ignite imaginations worldwide. So, the alien megastructure hypothesis became the most famous, and infamous, theory associated with Tabby's star. It wasn't the most likely, but it was the most compelling. And in that tension, between sober scientific skepticism and wide-eyed human wonder, the star found its place in both science and culture. Somewhere between the quiet rigor of astrophysics and the boundless realm of human imagination, Tabby's star transformed from a technical anomaly into a global obsession. The moment the words alien megastructure were uttered, no matter how cautiously, no matter how tentatively, the story of this strange star exploded far beyond the walls of scientific journals. Tabby's star had all the ingredients of a cultural phenomenon, a mystery with no easy answers, a potential link to intelligent life, and a narrative shaped by both professionals and citizen scientists. It became, in short, the perfect storm for public fascination. News outlets around the world rushed to cover it. Major newspapers ran front-page stories with tantalizing headlines: "Strange star might host alien megastructure." Popular science magazines dissected the possibilities, laying out scenarios of Dyson spheres, comet swarms, or exotic astrophysics. Television programs seized on the drama, producing sleek documentaries filled with CGI Dyson constructs orbiting a star in Cygnus. Talk shows invited scientists to explain the discovery, often simplifying the nuances but amplifying the intrigue. And in the digital sphere, the reaction was even more explosive. On Reddit, thousands of threads speculated about what might be happening around Tabby's star. YouTube channels devoted to astronomy, science fiction, and futurism generated millions of views by analyzing the dips in brightness and weighing competing theories. Podcasts produced entire episodes exploring the mystery, some inviting Tabitha Boyajian herself as a guest to explain the star's behavior. Twitter buzzed with excitement, jokes, and philosophical musings about whether we had just glimpsed alien engineering. What made Tabby's star so captivating wasn't just the possibility of aliens. It was the way the mystery refused to settle into a single neat box. Every time a new explanation was proposed, it seemed to fall short. Dust could explain some of the data, but not all. Comets worked in theory, but not on the observed scale. Instrument error was ruled out. The uncertainty itself was the hook. People love mysteries, and here was a live one unfolding in real time, with scientists themselves admitting, "We don't know what's going on." The openness of the scientific process also played a huge role in feeding public curiosity. Tabitha Boyajian and her colleagues didn't hide behind closed doors. They engaged openly with the world. They explained the challenges, shared updates, and even launched crowdfunding campaigns so the public could directly participate in monitoring the star. Thousands of people, donating to Boyajian's Kickstarter and later following observation reports, became a way to feel like they were part of the unfolding cosmic detective story. The mystery also inspired debates that stretched far beyond astronomy. Philosophers, futurists, and science fiction writers weighed in. Was it truly possible that we had stumbled upon evidence of a civilization so advanced that they were harvesting the power of their sun? If so, what would that mean for humanity's place in the universe? Conversely, if the explanation turned out to be something mundane, dust or debris, would the disappointment outweigh the wonder, or would we still celebrate the thrill of chasing one of the greatest cosmic what-ifs? This duality, wonder and skepticism, gave the story staying power. It wasn't like a single sensational discovery that makes headlines for a week and then fades. Tabby's star lingered because the mystery persisted. People tuned in for new studies, new data, new dips in brightness, eager to see whether the puzzle pieces might finally fit. And with each update, conversations reignited across blogs, forums, and media platforms. In a way, Tabby's star became a mirror for human curiosity itself. It showed how quickly people are drawn to mysteries that flirt with the possibility of intelligent life, how we crave narratives that mix science fact with science fiction. It also showed how modern media amplifies such mysteries, turning technical astrophysical anomalies into global talking points. But there was something deeper as well. At its core, the fascination with Tabby's star revealed a longing to not be alone. The possibility, however slim, that its dimming was caused by alien engineering resonated with people on a profoundly emotional level. It wasn't just an astronomical puzzle, it was an existential one. What if the dips were shadows cast by structures built by beings millions of years ahead of us? What would that say about our own future, our potential, and our destiny in the cosmos? This is why Tabby's star captured imaginations across so many domains. It wasn't confined to scientists or hobby astronomers. It was discussed in classrooms, debated in cafes, written about in essays, and featured in sci-fi stories. It was a living mystery that allowed everyone, from experts to casual stargazers, to dream about what lies beyond our world. Somewhere, amid the growing storm of public fascination, speculation, and sensational headlines about alien megastructures, the scientific community knew it had to put its instruments to the test. If Tabby's star was truly being obscured by something as extraordinary as colossal artificial structures, then perhaps there might be other signatures, subtle or strong, that could reveal the hand of intelligence. And so, naturally, all eyes turned to the search for extraterrestrial intelligence, SETI. The SETI Institute had long been humanity's ear to the cosmos. Founded on the belief that, if intelligent life exists elsewhere, it might attempt communication across interstellar distances, SETI has spent decades developing tools to sift through the cosmic noise for any sign of artificial signals. For SETI researchers, the case of Tabby's star was irresistible. Here was a star whose light curve defied every standard explanation. If there was ever a candidate worth checking for radio signals, whispers of another intelligence, this was it. In late 2015, shortly after Jason Wright and colleagues floated the alien megastructure hypothesis, SETI began its focus campaign. Using the Allen Telescope Array in Northern California, they trained dozens of radio dishes on Tabby's star. The array scanned a broad range of frequencies, from narrowband signals, which would be the most unambiguous signs of artificial origin, to wideband emissions that could suggest large-scale energy use. The idea was simple. If some advanced civilization really was building vast structures around their star, perhaps they also used powerful radio communications, or perhaps the engineering itself would leak detectable signals into space. The results? Silence. SETI detected nothing unusual. No narrowband pings, no repeating signals, no faint radio chatter drifting from the direction of Tabby's star. The star was, in the radio spectrum, as quiet as any other ordinary point of light in the sky. This wasn't entirely surprising. SETI researchers emphasized that the absence of radio signals did not prove the absence of aliens. A civilization might use technologies beyond our detection capabilities. They might not be broadcasting at all. Or, perhaps, they might not exist in the first place. But what it did show, definitively, was that Tabby's star was not shouting across the galaxy. The SETI involvement carried a powerful symbolic weight. It demonstrated that scientists were willing to test even the wildest hypotheses with rigor and transparency. While many astronomers were skeptical of the alien megastructure idea, they did not dismiss it outright. Instead, they followed the scientific method: propose, test, and see what the data reveal. In this case, the data revealed only silence, but silence itself is a form of answer. The investigation didn't stop there. Beyond the Allen Telescope Array, other observatories were recruited to listen. Breakthrough Listen, a multimillion-dollar project funded by billionaire Yuri Milner to supercharge SETI's search, also turned its ears toward Tabby's star in later years. Using the powerful Green Bank telescope in West Virginia and later other facilities, Breakthrough Listen scanned for signals across billions of radio channels. Once again, the results were the same: no signs of extraterrestrial transmissions. These null results carried an important lesson for both scientists and the public. They reminded everyone that science must be grounded in evidence, not hope or speculation. The media might latch onto the alien megastructure idea because it was exciting, but SETI's careful surveys helped temper that narrative. Extraordinary claims, as Carl Sagan taught, demand extraordinary evidence. And so far, the extraordinary evidence simply wasn't there. Yet, interestingly, SETI's role in this saga didn't dampen the public's fascination. If anything, it deepened it. The very fact that scientists had actually checked for alien signals, in direct response to the mystery, made Tabby's star feel even more like a live detective case. People were thrilled to learn that the question wasn't being ignored, that our species had, however briefly, leaned forward and listened with intent. And, of course, silence is not the end of the story. It leaves room for possibility. It leaves room for other explanations. It keeps the mystery alive. Somewhere in the vast distance between wonder and reality, the scientific community drew a careful line in the sand. The mystery of Tabby's star had captured imaginations worldwide, fueled in part by media excitement over the alien megastructure hypothesis, but astronomers knew that speculation alone could not solve the puzzle. They leaned on a principle that has been a guiding light in science for centuries: extraordinary claims require extraordinary evidence. From the very beginning, astronomers approached the strange case of Tabby's star with a mix of curiosity and caution. Yes, the dimming was bizarre. Yes, it defied the neat and tidy models of planetary transits. Yes, it raised tantalizing questions about what could possibly cause such irregular behavior. But science is not about leaping to the most exciting explanation. It is about ruling out every possible natural explanation before entertaining something as radical as alien engineering. To the broader public, this skepticism sometimes came across as disappointing. After all, it's far more thrilling to imagine colossal Dyson spheres than it is to consider clouds of interstellar dust. But to scientists, skepticism is not pessimism, it's discipline. It's the safeguard that prevents us from fooling ourselves. Throughout history, there have been countless examples where phenomena seemed inexplicable at first, only to later reveal perfectly natural explanations once more data was gathered. The pulsar, for instance, was jokingly dubbed LGM-1 for Little Green Men 1, when it was first discovered in 1967 because of its unusually regular radio pulses. But in time, those pulses were explained as emissions from rapidly rotating neutron stars. What once looked like evidence of alien intelligence turned out to be a brand new class of natural object. Astronomers drew on this history when discussing Tabby's star. They reminded the public, and themselves, that the universe is full of surprises, and often those surprises expand our understanding of natural processes without needing to invoke aliens. The priority, therefore, was to dig deeper into the data, to use every tool available to test hypotheses, and to resist the temptation of prematurely claiming something extraordinary. Tabitha Boyajian herself embodied this balance. While she openly acknowledged how baffling the light curve was, she always emphasized the need for careful, methodical work. In interviews, she repeatedly reminded people that the alien megastructure idea was the least likely explanation, even if it was the most glamorous. Her message was consistent: don't underestimate the creativity of nature. If we don't yet understand the cause, it doesn't mean the answer must be extraterrestrial, it just means our science hasn't caught up yet. This caution extended to every corner of the professional astronomy community. Papers were written exploring various natural scenarios: cometary swarms, planetary collisions, circumstellar dust, interstellar clouds, and even the possibility of intrinsic variability in the star itself. While none of these explanations fit perfectly, scientists preferred the imperfect natural hypothesis over their extraordinary artificial hypothesis, because history had taught them to trust nature first. The mantra "extraordinary claims require extraordinary evidence" became almost a refrain in discussions of Tabby's star. It wasn't a dismissal of the mystery, it was a framework for approaching it responsibly. After all, if we were truly to claim evidence of extraterrestrial intelligence, the burden of proof would be monumental. The evidence would have to be so robust, so unambiguous, that no natural explanation could stand against it. Nothing about Tabby's star, strange as it was, reached that threshold. And yet, the scientific skepticism did not diminish the star's importance. Quite the opposite, it elevated it. Tabby's star became a case study in how science works at its best, confronting a puzzling anomaly with open-minded curiosity, entertaining every possibility without rushing to conclusions, and allowing evidence to guide the way forward. It showed the world that scientists are neither cynics nor dreamers, but careful investigators who tread the fine line between imagination and rigor. This skepticism also served a valuable public function. In a media landscape eager to sensationalize, astronomers stood as voices of reason, reminding everyone that while the idea of alien megastructures was fun to speculate about, it was almost certainly not the case. Their caution was not meant to dampen wonder, but to protect truth. After all, claiming aliens prematurely and later being proven wrong would do more harm than good, not only to astronomy, but to the credibility of science itself. In the end, the cautious approach kept the conversation grounded. It invited the public to marvel at the mystery while still respecting the scientific process. It reframed the excitement away from maybe it's aliens towards something equally profound: we are watching science unfold in real time, and the universe is stranger than we imagined. Somewhere deep in the labyrinth of theories, after aliens were mostly set aside and comets began to lose credibility, a quieter but far more scientifically grounded idea began to emerge: dust. Not the shiny, solid kind of cosmic megastructures that captured headlines, but the fine, drifting particles that populate much of space, the sort of explanation that seemed, at first, almost too mundane for such a captivating mystery. Yet as the evidence piled up, the dust hypothesis grew into the leading contender for explaining the bizarre behavior of Tabby's star. To appreciate why dust became the frontrunner, we need to step back and think about what astronomers were seeing. Tabby's star wasn't just dimming, it was dimming in strange, uneven ways. Some dips lasted only a few days, others stretched across weeks, and at its most extreme the star's brightness fell by nearly 22%. No known planet could cause that, and no simple stellar process seemed to fit. But dust, tiny, irregular particles, had a certain flexibility as an explanation. Dust clouds can be unevenly distributed, patchy, and dynamic, which matched the unpredictable dips recorded by Kepler. What's more, dust doesn't block light the way a solid object does. If you place an opaque planet between us and its star, The dip in brightness is uniform across all wavelengths: infrared, visible, ultraviolet. But dust interacts with light differently. Smaller grains scatter shorter wavelengths of light more effectively, leading to uneven dimming across the spectrum. This effect is called chromatic dimming, and it's one of the key fingerprints astronomers look for when trying to identify whether dust is involved. And when Tabby's star was studied across multiple wavelengths, that's exactly what astronomers found. During dips, the star's light wasn't dimming evenly, it was dimming more in blue light than in red. That pattern is almost impossible to explain with a solid structure like a planet or megastructure, but it's exactly what you'd expect if fine clouds of dust were drifting across our line of sight. This finding didn't mean the case was closed, though. Dust could account for the chromatic dimming, but there were still puzzles to solve. For one, the dust had to be very fine, micron-sized grains or smaller, otherwise it would scatter light differently. But dust that's small doesn't survive long around a star. Radiation pressure and stellar winds tend to blow fine particles away quickly. So, if dust really was the culprit, it meant something had to be replenishing it continually. That raised new questions. What was producing this dust? Was it fragments from evaporating comets, remnants of a recent planetary collision, or something else entirely? Another piece of evidence pointing toward dust came from long-term monitoring. In addition to the short, sharp dips recorded by Kepler, astronomers noticed a gradual, century-scale dimming in the brightness of Tabby's star when they examined old photographic plates dating back to the 1890s. While that analysis was debated and later revised, it suggested that Tabby's star wasn't just experiencing temporary dips, it might also be undergoing a slower, more complex fading process. Dust, again, could explain this if large-scale clouds were passing between the star and Earth over decades or centuries. The dust hypothesis also aligned with what was not observed. If alien megastructures were blocking the light, astronomers expected to see signs of waste heat in the infrared spectrum. After all, enormous solar collecting machines would absorb energy from the star and re-radiate it as heat. But infrared studies showed no such excess. Tabby's star didn't glow with hidden warmth. That absence fit neatly with dust, which blocks light without necessarily re-emitting it in ways detectable from Earth. Despite its strengths, though, the dust hypothesis has never been a perfect fit. For example, while dust explains the wavelength-dependent dimming, it doesn't fully account for the sheer depth of some of the dips. Dimming of 20% or more would require an astonishing amount of dust. And yet, the star didn't show the thick infrared signature that would normally accompany such heavy obscuration. It was as if the dust was there, but incredibly fine, thinly spread, and ephemeral, making it very difficult to pin down. This is why Tabby's star remains such a tantalizing case. Dust explains a lot, but not everything. It's the explanation that fits best with the current evidence, but it still leaves lingering mysteries. Is the dust orbiting the star itself, or drifting in interstellar space between us and it? Is it the byproduct of comets, collisions, or some unknown process? Why does it create such dramatic and irregular dips compared to any other star observed so far? Still, most astronomers today consider dust to be the most natural and convincing explanation. It doesn't require rewriting the laws of astrophysics. It doesn't require aliens. It just requires complex, evolving dust clouds behaving in ways we haven't fully mapped out yet. And in science, the simplest explanation that matches the evidence usually wins. But the very fact that dust is ordinary shouldn't make it feel disappointing. If anything, it reveals how even the most basic building blocks of the universe, tiny particles drifting through space, can create phenomena so dramatic and mysterious that they challenge the limits of our understanding. Dust may not be exotic in itself, but the way it behaves around Tabby's star certainly is. Somewhere in the interplay of light and shadow, the case for dust over megastructures becomes most convincing. The heart of the mystery around Tabby's star lies not only in the sheer depth of its brightness dips, but also in the way those dips reveal themselves when examined across the electromagnetic spectrum. If a solid object, whether a planet, an asteroid, or even a vast alien megastructure, were passing in front of the star, it would block light uniformly. No matter what wavelength you observed, blue, red, infrared, the dip would look essentially the same. This is a cornerstone of exoplanet detection. A planetary transit produces a clean, achromatic dip, meaning all wavelengths are dimmed equally. But Tabby's star doesn't behave this way. When astronomers studied its dips with ground-based telescopes and compared them across multiple wavelengths, they discovered something striking: the dimming was wavelength-dependent. Blue light faded more strongly than red light. This is a classic telltale sign of dust. Tiny particles scatter shorter wavelengths, like blue light, more effectively than longer wavelengths, like red, producing exactly the uneven dimming pattern observed. This phenomenon, known as chromatic extinction, is the same basic effect that makes our own sky appear blue during the day and red at sunset. The atmosphere scatters blue light more efficiently. This wavelength-dependent dimming was the smoking gun that tipped the scales in favor of dust as the explanation for Tabby star's bizarre behavior. Megastructures, however intriguing they might sound, could not account for this chromatic variation. A giant alien solar collector would cast a uniform shadow, cutting off the same fraction of starlight across the spectrum. The fact that the dips weren't uniform strongly argued against anything solid, large, and opaque. Another layer of support for the dust hypothesis came from spectroscopic data. When astronomers split the star's light into its spectrum and examined it during dimming events, they found signatures consistent with fine-grained particles rather than solid bodies. Certain absorption features hinted at the presence of small dust grains, likely only a few microns or less in size. This level of detail made the case even clearer. Dust wasn't just a convenient explanation, it was one backed by direct spectral evidence. Still, this didn't mean the dust explanation was without challenges. For one thing, as I mentioned earlier, micron-sized dust doesn't hang around long in the harsh environment near a star. Radiation pressure and stellar winds tend to sweep it away. That means if dust is causing the dimming, it must be constantly replenished. Something, whether a swarm of comets disintegrating, a planet being pulverized, or even an unknown stellar process, must be feeding a steady supply of fine particles into the system. But whatever the source, the spectral and chromatic evidence pointed squarely toward dust being involved. The absence of an infrared excess was also crucial in dismissing megastructures. If alien collectors or large solid objects were surrounding the star, they would absorb starlight and re-emit it as heat, glowing brightly in the infrared. Sensitive observations from telescopes like NASA's Spitzer Space Telescope, however, found no such excess. Tabby star's infrared profile looked utterly ordinary, as though nothing massive or heat-emitting was lurking around it. Dust, on the other hand, especially very fine and thinly distributed dust, could dim light dramatically without creating a strong infrared signature. It was another way the dust theory fit the observations better than the megastructure idea. There's also a philosophical elegance in this. Dust is one of the most common materials in the cosmos. It is born in the deaths of stars, carried along in stellar winds, and scattered through galaxies. It is messy, patchy, and complex, and it often creates confusing signals for astronomers trying to peer through it. The fact that Tabby star's mystery likely boils down to dust is a reminder of how easily nature can outwit us, not through exotic, high-tech alien engineering, but through the subtle, chaotic behavior of ordinary matter. Yet, we can't ignore that dust still leaves us with big unanswered questions. Where exactly is this dust located, circling close to Tabby's star, spread through its outer system, or drifting somewhere in the interstellar medium between us and the star? What process could generate so much of it so consistently? And why does Tabby's star's light curve remain so uniquely bizarre when compared to the hundreds of thousands of stars observed by Kepler? Even if dust is the culprit, the details remain elusive, which keeps the star's aura of mystery alive. In the end, though, the case is clear. Dust simply fits the data better. The uneven dimming across wavelengths, the lack of infrared excess, and the spectral evidence all align to form a coherent picture. The megastructure idea, while captivating, doesn't hold up under this scrutiny. And while the dust explanation may seem ordinary compared to alien civilizations, it's extraordinary in its own way, because it forces us to rethink the dynamics of dust around stars and challenges us to refine our models of stellar environments. Somewhere in the dusty archives of astronomy, long before the digital age, lies another clue to the mystery of Tabby's star. This clue doesn't come from space telescopes like Kepler or infrared observatories like Spitzer. It comes from the ground, from old glass photographic plates exposed to starlight more than 100 years ago. These fragile records, stored in observatories for generations, preserve the brightness of stars as they appeared to astronomers in the late 19th and early 20th centuries. And when scientists went back and looked at these historical plates, they found something extraordinary. Tabby's star seems to have dimmed gradually over the course of a century. This long-term dimming adds a whole new layer of complexity to the mystery. Kepler showed us that the star's brightness could plunge suddenly by as much as 22% over a few days or weeks. But the Harvard Plate Archive, containing observations dating back to the 1890s, suggested that Tabby's star had also faded by about 15 to 20% over roughly 100 years. This isn't just a temporary dip caused by some passing cloud of debris. It's a slow, continuous fading that no other star of its type seems to exhibit. If true, this century-long decline is deeply puzzling. Stars don't normally dim like that on human timescales. Their life cycles are measured in millions or billions of years, and while variability exists, it typically follows predictable cycles or well-understood patterns. A star of Tabby's type, a main sequence F-type star, similar to but a bit hotter than our Sun, should be relatively stable in brightness. So why does it appear to be steadily fading over generations of observation? At first, this finding electrified the astronomical community. It suggested that whatever was happening around Tabby's star might not just be short-term dust clouds or comet swarms. It might be part of a much larger, longer-term process. If the fading is real, it could mean that the star's environment is undergoing changes on a scale we've never seen before. Perhaps vast amounts of material are slowly drifting in front of the star, or maybe the star itself is behaving in ways not accounted for in stellar models. However, science is cautious, and the long-term dimming evidence has been hotly debated. Critics pointed out that the old photographic plates were not designed for the kind of precision needed to measure centroscale brightness changes at the percent level. Factors like plate degradation, calibration errors, or changes in observing conditions could create false signals. When astronomers tried to repeat the analysis using other plate collections, the results weren't always consistent. Some studies suggested the dimming was real, others argued it was an artifact of imperfect data. Still, more recent, higher precision measurements from modern observatories seem to show that Tabby's star has indeed undergone decade-scale brightness trends. Between 2009 and 2013, during the Kepler mission, the star's baseline brightness appeared to drop by a few percent in addition to its sudden dips. Observations from ground-based telescopes later confirmed that the star wasn't entirely stable. It really was fading on timescales of years, not just days. This doesn't prove the century-long decline beyond all doubt, but it does suggest that the long-term dimming is not entirely an illusion. If we take the long-term fading at face value, what could it mean? Dust again rises as the leading candidate. Imagine enormous, diffuse clouds of dust slowly drifting across our line of sight, not dense enough to create sharp dips, but thick enough to gradually block a fraction of the star's light over decades. This would neatly connect the century-scale dimming with the short, sharp dips observed by Kepler. Together, they could be part of the same phenomenon, a complex and evolving dusty environment around the star. But this raises new questions. What's the source of so much dust? Cometary activity could produce it, but the sheer amount required would be staggering, far more than a few comets breaking apart. A planetary collision might generate enough debris, but such an event would be rare and dramatic. Or perhaps the dust isn't orbiting the star at all, maybe it's interstellar dust drifting between Earth and Tabby's star, a vast and uneven cloud slowly shifting over time. Another possibility, more speculative, is that the star itself is undergoing an unusual kind of intrinsic variability. Some stars do exhibit long-term changes in brightness, though usually for reasons we can explain, like magnetic cycles, pulsations, or structural changes in their outer layers. But for a star like Tabby's, no known mechanism predicts the slow fading seen in the data. If it is intrinsic to the star, it would mean we've uncovered an entirely new type of stellar behavior. This century-scale fading also intersects intriguingly with the alien megastructure hypothesis. If a civilization were gradually constructing a Dyson swarm around the star, you might expect the star's brightness to fade slowly over decades or centuries as more collectors were put into orbit. The historical dimming, in that sense, was seized upon by some as circumstantial support for the idea. Of course, as with all extraordinary claims, the alien scenario remains far less likely than dust or natural variability. But the fact that the long-term fading fits into multiple frameworks only makes the mystery richer. Whether the century-long dimming is perfectly real or partly an artifact, it has played a huge role in keeping the puzzle alive. If confirmed, it would make Tabby's star unique among the hundreds of thousands of stars studied with similar methods. No other star has shown the combination of sudden deep dips and slow, century-scale fading. It's this combination that makes it so difficult to explain with conventional astrophysics. Somewhere between the slow, almost imperceptible fading of Tabby's star over decades and centuries lies another, far more dramatic signature: the short-term dips that catapulted this star into astronomical fame. If the long-term dimming is like a dimmer switch slowly turning down the lights, these sudden plunges are like someone flicking the lights on and off unpredictably. And it was these very dips, observed with stunning precision by NASA's Kepler space telescope, that first revealed to astronomers just how strange this star really is. Kepler's job was simple but revolutionary: stare continuously at more than 150,000 stars, measuring their brightness with exquisite precision, looking for the tiny, periodic dips in starlight caused by planets crossing, or transiting, their stars. A typical exoplanet transit might dim a star by about 1% or less, and the dips repeat like clockwork as the planet completes its orbit. This method has given us thousands of confirmed exoplanets. But Tabby's star didn't follow the script. Instead of neat, repeating dips, Kepler recorded chaotic, irregular plunges in brightness. Some were shallow, only a fraction of a percent. Others were so deep they startled astronomers, up to 22% dimming, an amount that simply cannot be caused by a planet the size of Jupiter or even several planets combined. To put this in perspective, Jupiter crossing the Sun would block about 1% of its light from a distant observer. To reach 22%, you'd need something impossibly large, on the scale of thousands of planets, and that's not realistic. Even more puzzling, the dips had no consistent pattern. Some lasted a few days, others stretched over a week. Sometimes dips came in clusters, overlapping and blending into one another. Other times the star returned to normal brightness for long stretches before plunging again. The light curve looked less like the smooth heartbeat of planetary transits and more like an erratic, jagged graph of something wild and unpredictable. Astronomers tried to fit these dips into known astrophysical categories, but nothing worked. If it were planets, the dips would repeat on orbital timescales, yet no two dips lined up in a way that suggested periodicity. If it were a binary companion star eclipsing Tabby's star, the dips would be far more regular. If it were intrinsic variability within the star itself, such as pulsations or magnetic activity, the light curve would look entirely different from what Kepler recorded. Instead, the dips remained unique and unexplained, defying every conventional model. The contrast with the long-term dimming makes this star even more enigmatic. On one hand, you have a slow, steady decline in brightness that could plausibly be explained by a diffuse veil of dust. On the other hand, you have abrupt, massive plunges that suggest something far more concentrated and dramatic passing in front of the star. It's as if two separate phenomena are happening at once, one on century timescales and one on daily or weekly timescales, both layering together to produce a puzzle no one has yet solved. What makes the short-term dips so haunting is their sheer unpredictability. With planets, astronomers can predict exactly when the next transit will occur and how deep it will be. But with Tabby's star, no one can say when the next plunge will happen, how deep it will go, or how long it will last. Even with ongoing ground-based monitoring, astronomers sometimes catch a dip and sometimes don't, because the star simply refuses to play by the rules. This unpredictability is what fuels so much speculation and fascination. Adding to the intrigue, when researchers examined the wavelength dependence of the short-term dips, they found the same clue seen in the long-term fading. Shorter wavelengths, blue light, were dimmed more strongly than longer wavelengths, red light. This again points to dust, likely very fine-grained particles drifting in front of the star. But the short-term dips are so deep and abrupt that the dust must be clumpy, dense, or replenished in massive amounts to explain the data. It's not just a haze, it's as though large clouds of dust are crossing our line of sight, blotting out significant chunks of the starlight. And yet, even the dust explanation struggles to fully capture the complexity of the dips. To block 22% of a star's light, the dust cloud would have to be enormous. 2. Move across the star in just a few days. It would also need to be relatively close to the star and orbiting at high speed. But how could such large, massive structures remain coherent without dispersing quickly? Where is all this dust coming from? Could it be the remnants of a planet being torn apart by tidal forces, or a massive collision in the system producing debris on an epic scale? The interplay between the short-term dips and the long-term fading deepens the sense of mystery. Are they part of the same underlying process, or are they unrelated phenomena coincidentally happening in the same system? If the dips are caused by dust clouds from disintegrating bodies, perhaps the long-term fading represents the gradual spread of that material throughout the system. Or maybe the fading and the dips are separate clues pointing to an even larger, more complex scenario we haven't imagined yet. In astronomy, stars are often classified and understood by their light curves. The patterns of their brightness changes over time. For most stars, these curves fall neatly into categories we know well: pulsating stars, eclipsing binaries, flare stars, and so on. Tabby's star, with its erratic dips layered over a century of fading, doesn't fit anywhere. It's like finding a piece in the cosmic puzzle that doesn't match the picture on the box, and instead forces you to wonder if the picture itself is wrong. Somewhere in the brainstorming halls of astronomy, when Tabby's star refused to fit into any neat category, scientists began exploring a wide range of alternative theories. These ideas, while not as sensational as alien megastructures, attempted to ground the strange dimming events in natural astrophysical processes. From vast swarms of comets to shattered planetary debris fields, and even the possibility that the star itself was behaving in unexpected ways, researchers sifted through every option, hoping one would neatly explain both the short-term dips and the long-term fading. The first alternative that gained traction was the comet swarm hypothesis. Imagine dozens, or even hundreds, of giant comets on eccentric orbits around Tabby's star. As they swing close to the star, they heat up, shedding massive tails of gas and dust that could temporarily block large amounts of light. If enough comets crossed the star in close succession, the overlapping trails might produce the irregular and deep dips Kepler observed. This explanation had a certain appeal. Comets are known to generate significant amounts of dust, and their erratic orbits could naturally produce irregular patterns rather than periodic ones. However, this idea quickly ran into serious problems. To block up to 22% of the star's light, the comet swarm would have to be staggeringly massive, far beyond what we see even in the most active cometary systems in our own solar neighborhood. The dust tails would also need to align precisely with our line of sight, a very unlikely coincidence. And crucially, the comet hypothesis didn't do a good job of explaining the long-term fading that appears in historical records and modern observations. Cometary activity is typically chaotic and short-lived, not something that would dim a star consistently over a century. Another major theory focused on planetary debris, the aftermath of a catastrophic collision in the system. If two large planets or moons smash together, they could generate enormous clouds of dust and fragments. This debris, spiraling inward under the pull of the star's gravity, might periodically block large portions of the starlight. Over time, as the material spread out, it could also account for the gradual fading seen on longer timescales. Planetary collisions are thought to be relatively common in young planetary systems, and such events have even been hinted at in observations of other stars. But once again, Tabby's star presented challenges. The star doesn't appear especially young, making a recent planetary collision less likely. And if such a colossal collision had occurred, we'd expect to see significant amounts of infrared radiation from all the warm dust heated by the star's light. Infrared observatories, however, found no such excess. The system wasn't glowing in the infrared the way a debris-filled system should, casting doubt on this explanation. A third line of thinking turned inward, toward the star itself. Could intrinsic stellar variability, changes happening within Tabby's star, be responsible for the mysterious light curve? Some stars are known to fluctuate in brightness because of pulsations, star spots, or cycles in their magnetic activity. For instance, our own Sun has an 11-year activity cycle where sunspots and solar storms can affect its output slightly. Perhaps Tabby's star had some exotic form of variability never before documented. The problem is that Tabby's star is classified as an F-type main sequence star, a category known for relative stability. Stars like this don't generally show the kind of wild, irregular dips seen by Kepler. Pulsations tend to be periodic, not erratic. Star spots usually cause small, regular dips as the star rotates, not sudden plunges lasting several days. And while magnetic cycles might affect long-term brightness, they wouldn't normally produce the chaotic short-term behavior we see. If Tabby's star really is varying on its own, it would imply a completely new and unknown mechanism at work inside such stars, something not accounted for in current stellar models. Other fringe theories have also been floated. Some scientists speculated about massive rings of material around a giant planet in the system, rings so large they could block a big chunk of starlight if aligned just right. Others suggested that interstellar material, drifting between Earth and the star, might be intermittently crossing our line of sight. While intriguing, these ideas struggled with the same issue. The scale and irregularity of the dips are unlike anything we've ever recorded elsewhere, making each explanation incomplete. The truth is, none of these alternatives provide a single, neat solution. Comets can explain some aspects but fall short on scale. Planetary debris might account for sudden dips but doesn't match the lack of infrared signatures. Intrinsic stellar variability offers an elegant in-star explanation but clashes with what we know about F-type stars. Every time a theory gets close, another piece of the puzzle refuses to fit. What this process illustrates, though, is the scientific method in action. Astronomers didn't leap straight to wild conclusions. They explored every natural explanation they could imagine. Each hypothesis tested against the data helped refine our understanding of what Tabby's star is not, narrowing the field of possibilities. And even when theories failed, they often sparked new insights into how stars, dust, and planetary systems evolve. Somewhere in the search for answers, the comet swarm hypothesis emerged as one of the earliest serious attempts to provide a natural explanation for the bizarre light curve of Tabby's star. On paper, it had an intuitive appeal. Comets are messy, irregular objects. They throw off long tails of dust and gas as they approach their star. Unlike planets, their orbits can be eccentric, unpredictable, and prone to clustering. So, if you imagine not one or two comets, but dozens or even hundreds, passing in front of Tabby's star, you might picture exactly the kind of jagged, irregular dips Kepler observed. At first, this seemed like a compelling way to avoid invoking exotic or extraordinary explanations. Astronomers proposed a scenario in which a family of comets, perhaps disturbed by a passing star or gravitational perturbation within the system, plunged toward Tabby's star, shedding vast plumes of dust. These plumes, aligned along our line of sight, could in theory overlap to produce the deep, irregular drops in brightness Kepler recorded. But as soon as researchers began to calculate the details, the comet swarm idea began to crack under the weight of the evidence. The most glaring problem is scale. The deepest dips observed by Kepler reached about 22%, a colossal reduction in brightness. A typical comet, even with an enormous tail, would block only a tiny fraction of starlight. To reach the observed levels, you would need an absurd number of comets, each many kilometers across, arranged in just the right way. One study estimated that you'd need thousands upon thousands of giant comets all sweeping across the star in rapid succession. That's not just unlikely, it's almost impossible. Next comes the issue of irregularity. While comets can certainly produce erratic signatures, the specific pattern Kepler observed doesn't quite fit what we'd expect from a swarm. Some dips were sharp and shallow, others deep and prolonged, and they came in unpredictable clusters. A comet family, no matter how large, would likely create more consistent or at least somewhat traceable structures in the light curve. Instead, Tabby's star gave us a wildly chaotic signal, with no clear periodicity, orbital pattern. Another serious challenge to the comet hypothesis is the infrared problem. Dust and gas shed by comets absorb starlight and re-radiates it in the infrared spectrum. If Tabby's star were surrounded by colossal clouds of comet dust, infrared telescopes should have picked up a strong excess emission, glowing from the warmed material. Yet observations from infrared surveys, including NASA's Spitzer Space Telescope, showed no such excess. Tabby's star wasn't surrounded by the kind of glowing debris we'd expect if comet activity were responsible for both the dips and the long-term fading. The comet theory also struggles to explain the long-term dimming. Historical records suggest Tabby's star has faded steadily over the past century, and ongoing monitoring confirms gradual brightness changes. A comet swarm might cause dramatic short-term events, but comets are transient phenomena. Their tails dissipate quickly, and the dust they produce disperses into space. They cannot plausibly account for a dimming trend lasting decades or centuries without requiring an implausibly endless supply of new comets constantly replenishing the dust clouds. There's also the problem of likelihood. Our solar system does have comets, but massive coordinated swarms of thousands of giant comets are vanishingly rare, if not outright improbable. The scenario requires an extraordinary chain of events, perhaps a passing star disturbing a distant Oort cloud-like region around Tabby's star, sending in waves of comets. While possible in theory, The odds of us observing such a system in just the right alignment, at the exact right time, are slim. Finally, when researchers modeled how a swarm of comets would look in a Kepler light curve, the simulated patterns just didn't match the data. The dips from comets were too shallow, too smeared out, and too inconsistent with the sharpness of some of Tabby's star's plunges. As a result, most astronomers gradually set aside the comet hypothesis as insufficient. It was a creative and promising idea, but the more data poured in, the less it fit. This doesn't mean comets play no role at all. It's possible smaller cometary activity contributes some dust or enhances the irregular dimming. But as a primary explanation, the comet swarm theory simply cannot carry the weight of the observations. The scale is too vast, the patterns too irregular, and the missing infrared glow too damning. What the comet hypothesis did accomplish, however, was important. It reminded astronomers that the universe is capable of strange and chaotic dynamics. It pushed researchers to consider natural, dust-based mechanisms and opened the door to broader thinking about how planetary debris, collisions, or even entirely new processes could shape a star's light curve. In that sense, even though comets likely aren't the full answer, they helped guide the search for more plausible explanations. Somewhere in the story of Tabby's star lies a truth bigger than just one strange star. It's about how we find such mysteries in the first place. Tabby's star wasn't stumbled upon by someone pointing a telescope on a random night. Instead, it emerged from the oceans of data produced by NASA's Kepler Space Telescope, one of the most ambitious missions in the history of exoplanet science. And this makes Tabby's star a perfect example of how big data in astronomy doesn't just confirm what we expect, it reveals things we never imagined. The Kepler mission was designed to answer a deceptively simple question: how common are planets around stars? To tackle that, Kepler stared at a single patch of sky, monitoring the brightness of about 150,000 stars simultaneously over the course of years. Every star's light curve, its record of brightness over time, was tracked with exquisite precision, creating a treasure trove of data. The mission's main goal was to look for tiny, periodic dips caused by planets passing in front of their stars. But the sheer volume of data Kepler produced, terabytes upon terabytes of light curves, meant that its value went far beyond just planet hunting. Within those datasets, astronomers realized, might be all kinds of astrophysical phenomena: binary star interactions, stellar flares, pulsations, or even things they had never predicted. Tabby's star was a case in point. Here was a star that didn't fit the expected mold. If Kepler had only been programmed to flag neat, regular, planet-like dips, Tabby's star might have been dismissed as noise or an anomaly. But because researchers and volunteers were combing through the dataset with open eyes, they stumbled upon something extraordinary. It was citizen scientists, after all, who first raised the alarm that this star's light curve didn't look like anything they'd seen before. Without such vast data collection, and without the willingness to look beyond the mission's primary goal, Tabby's star might still be hidden in the numbers. This highlights one of the greatest strengths of big data in astronomy: its potential for serendipity. When you record vast amounts of information across thousands of objects, you increase the odds of encountering something that defies existing categories. Instead of finding only what you're looking for, you also uncover the unknown unknowns, the surprises that push science forward. Tabby's star is a textbook case, a bizarre outlier in a dataset designed for an entirely different purpose. The discovery also underscores the growing importance of human-computer collaboration in science. Algorithms are excellent at spotting the clean, periodic dips of exoplanets, but Tabby's star required human intuition. Volunteers from the Planet Hunters project noticed its odd light curve because it looked weird, something algorithms weren't trained to catch. This interplay between computational brute force and human pattern recognition is becoming a hallmark of modern astronomy. In a way, Tabby's star wasn't just discovered by Kepler, it was discovered by the combination of big data and human curiosity. Another lesson here is the value of archival science. Kepler's data remains available to the public, and researchers continue to sift through it, often years after the spacecraft stopped collecting new observations. Tabby's star teaches us that the first pass through a dataset doesn't exhaust its potential. Hidden gems may lie buried in the noise, waiting for someone with a fresh perspective or a new algorithm to bring them to light. And there's a bigger picture. Tabby's star hints that the universe might be filled with phenomena we haven't even thought to imagine yet. If one star out of 150,000 can behave this strangely, How many more surprises are hidden among the billions of stars we haven't monitored with such precision? Kepler's data was just a drop in the cosmic bucket, and already it delivered something unprecedented. This suggests that as surveys grow larger, like those planned with the Vera C. Rubin Observatory and other next-generation telescopes, the odds of encountering even more baffling mysteries rise dramatically. Big data doesn't just expand what we know, it expands our capacity to be surprised. It forces scientists to keep an open mind, to accept that not every light curve will fit neatly into the boxes of planet or binary or variable star. Instead, some, like Tabby's star, demand new theories, new tools, and sometimes entirely new ways of thinking about how stars and their environments behave. In that sense, Tabby's star is more than just an astronomical oddity. It's a case study in why we collect massive datasets in the first place. The payoff isn't just in the expected discoveries, the new planets, the stellar systems, but in the outliers that force us to confront the limits of our knowledge. Somewhere in the timeline of Tabby's star's mystery, once the Kepler spacecraft completed its mission and handed the baton back to the scientific community, the question became, what now? How do you continue unraveling the enigma of a star whose behavior defies easy categorization? The answer lay in ground-based monitoring, a global, collaborative effort to keep eyes on the sky and track every flicker of brightness from this most unusual star. The importance of ground-based monitoring cannot be overstated. Kepler provided an unprecedented data set, but it had limitations. It was a space-based telescope staring at one patch of sky for a finite period of time. Once its primary mission ended, Kepler couldn't keep recording Tabby's star indefinitely. Yet the star's story was far from over. Astronomers knew they needed long-term monitoring, spanning years or even decades, to see whether the strange dips in brightness would recur and whether new patterns would emerge. Enter Earth-based telescopes. Across the globe, from professional observatories to small university facilities, astronomers began scheduling regular observations of Tabby's star. Networks like the Lascaux Observatory Global Telescope, or COGT, which operates a distributed set of robotic telescopes around the world, became critical. These telescopes could monitor the star nearly continuously, passing the task from one location to another as Earth rotated. This global reach allowed astronomers to catch dips in real time, instead of relying on the chance alignment of space missions. One of the landmark moments in this monitoring effort came in 2017, when Tabby's star once again began to dim. By then, the world was watching closely. Professional telescopes, amateur astronomers, and even backyard stargazers equipped with modest CCD cameras were all tuned in. When the dips occurred, data poured in from around the planet. Unlike Kepler's solitary stream of light curves, this time, dozens of instruments were capturing the changes from different vantage points and in multiple wavelengths. This distributed monitoring was vital because it enabled scientists to not only confirm that the dips were real and not an artifact of a single instrument but also to study them in far greater detail. For example, telescopes could observe in different colors of light, tracking whether the dimming was wavelength dependent, a key clue that helped strengthen the dust hypothesis. With each event, researchers gathered new evidence about the composition of whatever was blocking the star's light. What makes this effort even more remarkable is the community-driven nature of the monitoring. Tabby's star had become such a public fascination that even non-professional astronomers wanted to contribute. Crowdfunding campaigns supported professional observing time, while citizen scientists contributed their own data. The star became a rare case where the public, amateurs, and professionals all worked side by side, united by curiosity. This democratization of science turned Tabby's star into one of the most watched stars in the sky. Long-term ground-based monitoring also helped address one of the lingering questions from the Kepler data. Was the star undergoing long-term dimming trends in addition to the short-term dips? By stitching together observations from the past century with ongoing ground-based work, astronomers could refine their models and test whether Tabby's star's behavior was continuing to evolve in subtle ways beyond the dramatic plunges. And there's a practical aspect, too. Ground-based telescopes are flexible. Unlike space missions, which are costly and rigidly scheduled, Earth-based observatories can pivot quickly. When Tabby's star starts dimming, telescopes around the world can be pointed at it within hours, ensuring no event goes undocumented. This agility ensures that the star remains under constant watch, like a patient whose condition must be monitored regularly to understand the progression of symptoms. Perhaps most importantly, Ground-based monitoring keeps the mystery alive. Kepler gave us the first act of the drama, but Earth's telescopes continue the story in real time. Each new dip is like a fresh plot twist, inviting new interpretations and rekindling debates about what could be happening around the star. Without this continuous vigilance, Tabby's star might have faded into obscurity after Kepler. Instead, it remains an active field of research, a live puzzle astronomers are still piecing together. This global network of telescopes, professional and amateur alike, is a testament to how far astronomy has come. We live in an era where a single strange star can mobilize the planet's scientific resources, all working together to monitor the faint flickering of light from a distant sun 1,470 light-years away. In many ways, Tabby's star is as much about collaboration and persistence as it is about astrophysics. Somewhere in the unfolding drama of Tabby's star, astronomers realized that if they wanted to test some of the most exotic ideas, including the jaw-dropping possibility of an alien megastructure, they needed to move beyond visible light. Visible light told us when the star dimmed and how much it dimmed, but it couldn't alone reveal the nature of what was blocking that light. For that, scientists turned to the infrared spectrum, a domain of light invisible to human eyes but critical for detecting heat. The logic was straightforward. If something as massive as a Dyson sphere or any other alien megastructure were orbiting Tabby's star, it wouldn't just block starlight. It would also absorb a tremendous amount of the star's energy. And just like anything that absorbs energy, it would re-radiate some of it back out. Specifically in the form of heat. That heat would glow in the infrared wavelengths, which telescopes on Earth and in space can detect. So, if giant alien solar collectors or vast solid panels surrounded Tabby's star, astronomers expected to see a distinct excess of infrared light pouring out. But when infrared studies were carried out, using facilities such as NASA's Spitzer Space Telescope and the Infrared Astronomical Satellite, IRAS, data from decades earlier, the results were crystal clear. There was no significant infrared excess. The star looked like a perfectly ordinary F-type star in the infrared. No extra warmth, no glow, no evidence of a vast heat-emitting structure in orbit. This was a devastating blow to the alien megastructure hypothesis, at least in its simplest form. A Dyson sphere, whether complete or partial, should light up the infrared sky like a beacon. Its absence argued strongly against that scenario. It also meant that other possibilities, dust, comets, or stellar variability, moved higher on the list of contenders. Yet the lack of infrared excess introduced a new challenge. If dust were responsible, why didn't it heat up and shine in infrared the way dust typically does? Normally, cosmic dust grains orbiting close to a star absorb light and re-emit it as heat. But in the case of Tabby's star, astronomers saw only the faintest hints of such emission, nothing on the scale that could explain massive clouds of material. This suggested that if dust was responsible, it had to be made of very fine particles that dispersed quickly or perhaps was colder and farther from the star than expected. To refine this, astronomers carried out multi-wavelength observations, looking at the dips not just in visible light but across the electromagnetic spectrum. They discovered something crucial: the dimming was wavelength dependent. Blue light was blocked more than red light. This was exactly the sort of behavior you'd expect from dust grains, which scatter shorter wavelengths more effectively than longer ones. A solid megastructure, on the other hand, would block all wavelengths equally, creating a flat dimming pattern. So, the infrared evidence painted a picture consistent with dust but inconsistent with alien megastructures. It didn't close the case completely. After all, one could argue for exotic megastructures designed to emit little heat or cleverly engineered to disguise themselves. But scientifically, the burden of proof shifted. Dust became the simpler, more natural explanation. But what makes this story fascinating is not just the result but the method. Infrared astronomy represents one of the most powerful tools we have for testing extraordinary claims. When astronomers first heard whispers about Dyson spheres, they immediately knew where to look: in the heat signature. The fact that Tabby's star failed to show one is an elegant example of science at work. Instead of getting carried away by speculation, researchers gathered data in another wavelength, tested the idea, and let the evidence speak. It also highlights why multi-wavelength astronomy is so vital. If we relied solely on visible light, the alien megastructure idea might still be alive and well. But by widening the lens to include infrared, scientists could rule out the most sensational interpretations and focus on more grounded explanations. Each wavelength tells a different part of the cosmic story, and only by combining them do we get the full picture. Still, the absence of infrared emission didn't solve the mystery completely. It left unanswered questions. If dust was causing the dimming, why wasn't it producing the level of heat we'd expect? Was the dust unusually thin or perhaps composed of exotic materials? Could it be interstellar rather than circumstellar, floating between us and the star, instead of around the star itself? The answers weren't clear, and they kept the debate alive. In the end, infrared studies gave us a vital constraint. No large warm structures are present around Tabby's star. This doesn't mean we know exactly what is there, but it narrows the field of possible explanations. It's like being told what the mystery isn't before being told what it is. And in science, ruling things out is often just as valuable as confirming them. Somewhere deeper in the search for answers, after visible light monitoring and infrared studies had ruled out some of the most sensational ideas, astronomers knew they had to peel back yet another layer of detail. Light curves told them how much the star dimmed and when it dimmed. Infrared measurements told them what kinds of large, warm objects weren't there. But to truly probe the makeup of whatever was interfering with Tabby's star's light, they needed to break down that light into its spectrum, the cosmic equivalent of a fingerprint. This is where spectroscopy came in, and it proved to be one of the most revealing tools in the entire investigation. By splitting starlight into its component colors, essentially spreading it out into a rainbow, astronomers could study how different wavelengths were absorbed or scattered during the dips. Subtle patterns in that rainbow revealed information about the size, composition, and distribution of whatever material was passing in front of the star. During several of the dimming events that followed Kepler's discovery, ground-based telescopes captured high-resolution spectra of Tabby's star. What they found was fascinating. The dimming was not uniform across all wavelengths. Instead, blue light was blocked more strongly than red light. This effect is known as chromatic dimming, and it's a dead giveaway for dust. Fine dust grains scatter short wavelength light, blue, more effectively than long wavelength light, red. If the dips had been caused by a solid object, such as a planet or an alien structure, the dimming would have been gray. All colors of light would have dropped equally. But here, the data spoke clearly. The fingerprints pointed to fine, submicron dust particles. These grains are so tiny that they can be pushed around by the star's radiation pressure, making them unstable over long periods. This matched another piece of the puzzle. If such dust were responsible, it would need to be replenished constantly, since it wouldn't survive long in orbit. That led to new questions. Where was the dust coming from? Was it being generated by evaporating comets? By collisions between planetesimals? Or perhaps by some unusual stellar activity? The spectra also gave astronomers the chance to look for specific chemical signatures. For instance, when dust passes in front of a star, it sometimes carries with it gas that leaves absorption lines in the spectrum. Thin dark bands that correspond to elements like sodium or calcium. While some hints of gas were detected, the patterns weren't as strong or consistent as one might expect if the star was surrounded by thick clouds of material. This suggested that whatever was causing the dips wasn't a dense, permanent disk, but rather transient, thin clouds of dust that appeared irregularly. These results were crucial because they closed off another loophole in the megastructure idea. Advocates of the Dyson sphere hypothesis had suggested that advanced civilizations might construct structures that don't radiate much heat, cleverly masking their presence. But spectroscopy undercut that argument. The wavelength-dependent nature of the dimming wasn't consistent with solid structures, no matter how advanced. Light scattering by dust was simply a better fit. Another intriguing aspect was that spectroscopy didn't just reveal dust, it hinted at diversity in the dust itself. Not all dips looked the same. Some had stronger wavelength dependence than others, suggesting that the dust grains varied in size from one event to another. This variability made the system look less like a uniform, stable disk and more like a chaotic, evolving environment. Perhaps a system still in turmoil, shedding debris from comets, asteroids, or other bodies. Spectroscopy also tied directly into the broader theme of long-term versus short-term behavior. If the star was undergoing centralong dimming trends, then perhaps larger, colder dust structures were drifting through our line of sight over decades. Meanwhile, the sudden sharp dips could be caused by smaller, temporary clouds of fine grains released by more localized events. Spectra provided a bridge between these scales, showing that both processes could leave their imprint in the star's light. And beyond the dust question, the use of spectroscopy for Tabby's star highlighted just how far astronomy has come. A century ago, astronomers could only note that a star looked dimmer than before. Today, we can dissect its light with such precision that we can tell whether the particles causing the dimming are submicron in size or closer to a grain of sand. That level of detail transforms the mystery from pure speculation into a testable, data-driven puzzle. The conclusion from spectroscopy wasn't that the mystery was solved. Far from it. But it provided a strong, science-based answer to one of the biggest questions. What could possibly block this much light without glowing in infrared? The answer: very fine, transient dust grains, spread thinly enough to evade strong infrared detection, but abundant enough to scatter visible light dramatically. Somewhere in the enormous catalogue of stars studied by astronomers, countless light curves have been plotted, examined, and compared. Stars pulse, flare, eclipse each other in binary systems, and host planets that transit in front of them with clock-like precision. But among all these stars, hundreds of thousands scrutinized by NASA's Kepler Space Telescope and countless more examined with Earth-based telescopes, none behave quite like Tabby's star. That uniqueness is one of the central reasons this mystery has held astronomers, citizen scientists, and the public in rapt attention for so long. To understand what makes Tabby's star stand out, let's first look at how predictable most stars are. When a planet passes in front of its host star, the light curve, the plot of brightness over time, shows a clean dip that's both shallow and regular. Every transit is nearly identical, because planets orbit on well-defined paths. Binary star systems, too, produce light curves with dips, but those are also neat and repeating, tied to the orbital cycle of one star eclipsing the other. Even stars with flares or variable brightness tend to follow known patterns. Pulsating stars brighten and fade on predictable cycles, and flare stars spike sharply before returning to their baseline. Now, contrast all that with Tabby's star. Its light curve looks like no textbook example. Instead of neat, repeating patterns, we see chaotic and irregular dimming events. The dips range from just a few percent in brightness to a staggering 22%, which is far too deep for a planet-sized object. The timing is erratic. Sometimes there are clusters of dips close together, sometimes long stretches of relative calm. Some dips are shallow, others are deep, and their shapes vary. Some are smooth, while others are jagged or asymmetric. There is no periodicity that matches the orbital mechanics of planets or binary companions. It's like comparing the heartbeat of a healthy patient to an EKG reading that makes doctors scratch their heads. But it doesn't stop there. Tabby's star doesn't just show these bizarre short-term dips. It also appears to undergo long-term fading across decades and even a century. When astronomers dug into old photographic plates, they noticed that Tabby's star seemed to have dimmed overall by as much as 15 to 20% over the past 100 years. Imagine a light bulb not just flickering erratically but also slowly dimming as though something were drawing a veil across it. That combination, erratic, sharp dips on short timescales and a slow, steady decline over the long term, is completely unprecedented. To put this in perspective, no other star among the nearly 200,000 stars monitored by Kepler displayed a similar pattern. Planetary transits, eclipses, stellar variability, all of those are well documented. But a star dimming by more than 20% with irregular timing and no apparent periodicity, Tabby's star is in a category of one. That uniqueness made astronomers cautious, but it also made them excited. When the natural explanations don't immediately fit, that's often when the most interesting discoveries are made. The uniqueness also magnifies the mystery. If dozens of stars behave this way, we'd already have a new class of stellar variability to study. But because Tabby's star is the only one, at least so far, it raises the question: is this just an extreme outlier of a known phenomenon, or are we seeing something entirely new? Could it be that Tabby's star represents a rare stage of stellar or planetary system evolution that we just happen to catch? Or does it point to some astrophysical process we haven't even theorized yet? Its uniqueness also helps explain why the alien megastructure idea gained such traction. When scientists see something that doesn't fit any existing category, imaginations run wild. The thought was, maybe we've stumbled upon evidence of intelligent life precisely because nothing else in the universe looks like this. That hypothesis didn't survive detailed scrutiny, but the uniqueness of the data is what made such bold speculation seem plausible in the first place. Beyond the scientific mystery, the star's singularity has cultural importance, too. Human beings are naturally drawn to the exceptional, the rare, the one-of-a-kind. Tabby's star is the cosmic equivalent of a fingerprint with no match in the database. It doesn't fit into our catalogue of stellar behaviors, and that makes it irresistible. Astronomers, journalists, and the public latched onto it not just because it was strange, but because it was uniquely strange. And this uniqueness continues to drive observations. Even years after Kepler's initial discoveries, telescopes around the world still turn their eyes to Tabby's star. Every time it dips again, astronomers scramble to gather more data, hoping that one more clue will unlock the secret. Other stars might fade a little, or flare a little, but none make the global community of scientists and skywatchers leap into action like Tabby's star. It has become a sort of cosmic celebrity, precisely because it refuses to behave like anything else. Somewhere at the intersection of mystery and discovery, Tabby's star didn't just become an astronomical curiosity. It reshaped the way scientists thought about exoplanets, stellar systems, and the surprises hidden in vast datasets. Before its discovery, the Kepler mission had already revolutionized astronomy by proving that planets are everywhere. Thousands of worlds had been identified, many with neat, predictable dips in starlight that matched our models beautifully. The narrative was comforting. Kepler would find Earth-like planets orbiting Sun-like stars, and science would neatly expand its catalogue. But then came Tabby's star, and suddenly the narrative wasn't so simple anymore. Its bizarre light curve, the deep, irregular dips and long-term fading, forced astronomers to ask questions they hadn't planned on. Up until then, the framework was straightforward. Stars dim when planets pass in front of them, and the light curves are clean and repetitive. Tabby's star shattered that expectation. It was a loud reminder that the universe is under no obligation to follow our scripts. This had a profound impact on exoplanet science. Scientists began to realize that Kepler's dataset, and future datasets from missions like TESS and Plato, might hold far more than just exoplanets. Kepler wasn't only a planet hunter, it was a treasure chest of stellar oddities. Tabby's star taught astronomers to broaden their vision, to look for outliers and anomalies, not just neat planet transits. After all, if one star could behave in such a bizarre and unprecedented way, who's to say there weren't more waiting to be discovered? The case also pushed researchers to refine their tools. Algorithms designed to detect regular transits might dismiss a star like Tabby's as noise or false positives. But human eyes, through the Planet Hunters project, saw the strangeness and refused to ignore it. This highlighted the importance of combining big data analytics with citizen science and human curiosity. Without that combination, Tabby's star might have slipped through the cracks as just another odd entry in a massive database. And there's another subtle impact. It expanded the definition of what exoplanetary systems could look like. Before, the mental picture was simple: a star orbited by one or more planets, maybe with some asteroid belts or cometary clouds. But Tabby's star suggested systems could be far messier. Perhaps collisions between planets or swarms of comets could create clouds of dust that obscure starlight. Perhaps stars go through poorly understood phases of variability that we've never modeled. The case forced scientists to consider far more chaotic and dynamic scenarios than the neat orbital clockwork we like to imagine. For exoplanet science, this was a necessary nudge. Too often, science can fall into the trap of looking only for what it expects to see. Kepler had been designed to detect Earth-like planets, but Tabby's star reminded everyone that discoveries don't always fit into preconceived boxes. It was a cosmic curveball that expanded the field from a narrow focus on finding planets to a much broader goal: understanding all the strange ways starlight can vary and what those variations reveal about cosmic environments. The influence even reached the philosophy of science. Tabby's star became a case study in how astronomers handle anomalies. Do we dismiss them as outliers? Do we jump to extraordinary explanations, like alien megastructures? Or do we carefully build new models to test against the data? It became an example used in classrooms and conferences alike, a reminder that while the hunt for planets is exciting, the hunt for the unknown is equally vital. Another practical impact is how researchers now approach data archives. Kepler may have finished its mission, but its data is still being combed through. Thanks to Tabby's star, astronomers are more attuned to the possibility of finding weird signals buried in the noise. This mindset influenced how future missions are planned: more flexible data processing, better handling of irregular patterns, and an openness to surprises that don't match expectations. And finally, there's the cultural impact on exoplanet science. Tabby's star made the field more visible to the public, not just because of the alien megastructure buzz, but because it embodied the thrill of encountering the unknown. It wasn't just another exoplanet, it was a puzzle that no one could solve. That captured imaginations worldwide and drew new attention to the science of exoplanets. The public saw that astronomy isn't always about neat answers, it's about wrestling with mysteries, sometimes for decades. In short, the case of Tabby's star broadened the horizon of exoplanet science. It reminded researchers that stars are more complex than we thought, that planets are only one part of the cosmic picture, and that big data hides surprises that algorithms alone may miss. It expanded both the scientific and cultural scope of the field, showing that anomalies aren't distractions, they're opportunities. Somewhere in the unfolding story of Tabby's star, even after years of observations, countless hours of data crunching, and passionate debate in both the scientific community and the public sphere, one thing has become abundantly clear: the puzzle is not fully solved. Dust may be the leading explanation, but Tabby's star continues to defy simple categorization. It is still whispering mysteries to us, and astronomers are listening intently. The dust hypothesis gained traction because it accounts for many of the star's unusual behaviors. Spectroscopic studies revealed that during dimming events, shorter wavelengths of light were absorbed more strongly than longer wavelengths. That's exactly what we'd expect if fine-grained dust particles were passing in front of the star, scattering blue light more than red. This color signature is the smoking gun that tilted the consensus toward dust. It elegantly explains why the dips aren't sharp-edged, as they would be if caused by planets or megastructures, but instead look smoother, irregular, and variable. But here's where the continuing puzzle lies. Dust alone doesn't explain everything. For one, the sheer depth of some of the dips, up to 22% dimming, poses a major challenge. To block that much starlight, the dust cloud would need to be incredibly dense, and yet infrared studies show no strong signs of warm dust radiating heat around the star. If massive amounts of dust were consistently present, astronomers should see its thermal glow. They don't. This contradiction is one of the central unresolved tensions. Another issue is the long-term fading. Archival data suggest Tabby's star has dimmed overall over the last century. That's not easily explained by passing dust clouds, which are expected to cause temporary dips, not century-long trends. Was the fading real, or could it have been an artifact of old photographic plates? Some researchers argue that the data calibration from those early observations might have introduced errors. But others point out that even modern monitoring hints at secular dimming, meaning the star's baseline brightness might genuinely be decreasing. If true, dust alone seems insufficient to account for this long-term behavior. Then there's the question of where the dust is coming from. If it's circumstellar, meaning orbiting the star, it should eventually either spiral into the star or disperse into space. To keep dimming over years and decades, the star would need a sustained source of replenishment. Maybe collisions between comets or planetesimals are generating fresh dust clouds. But no one has detected strong evidence of such catastrophic activity on the necessary scale. If the dust is interstellar, drifting between stars and coincidentally in our line of sight, then why is Tabby's star the only one showing such dramatic effects, given the vast number of stars in similar regions of the galaxy? The irregularity of the dips also remains hard to fully reconcile. Dust can explain uneven dimming, but the timing of Tabby's dips doesn't follow any consistent pattern. Unlike periodic transits or even recurring comet swarms, the events happen with chaotic spacing. That suggests a highly dynamic system, but one we don't yet fully understand. The continuing puzzle isn't just about the dust itself, it's about the possibility that multiple mechanisms are at play. Maybe Tabby's star is experiencing a rare combination of factors, some circumstellar dust from disintegrating bodies, some interstellar clouds drifting past, and perhaps even intrinsic variability in the star itself. A patchwork explanation could fit the data, but stitching it together convincingly remains an ongoing challenge. And then there's the emotional heart of the puzzle. Tabby's star continues to sit at the crossroads between the known and the unknown. Astronomers have solved enough of the mystery to rule out alien megastructures, but not enough to feel confident they understand every quirk. The result is a star that resists closure. Every new dataset provides hints but not final answers. For a scientific community that thrives on precision and predictive power, that can be both frustrating and exhilarating. The persistence of the mystery keeps Tabby's star at the forefront of research. Unlike many anomalies that fade into obscurity once partially explained, this star continues to demand attention. Its story is updated year by year as new observations are made, and while dust may be the best fit model, it is not a complete one. Something more is happening here, whether it's a rare astrophysical process, a unique configuration of material around the star, or simply a phenomenon we haven't even imagined yet. In many ways, the continuing puzzle is the most exciting part of Tabby's star's legacy. It reminds us that even in the age of high-tech telescopes and massive data archives, the universe can still surprise us with enigmas that defy easy answers. Science thrives on puzzles like this. They are the seeds of future discoveries. Somewhere deep within the ongoing enigma of Tabby's star lies a truth that reaches far beyond one peculiar object in the constellation of Cygnus. It's a truth about the very nature of science itself, that mysteries are not failures, but invitations. Tabby's star, so unpredictable, so defiant of easy explanations, has become a living reminder that the universe does not conform neatly to human expectations, and that our models, as sophisticated as they may be, are always provisional. Every unexplained anomaly is a call to refine, re-examine, and sometimes even overturn the assumptions we hold about how the cosmos works. For astronomers, Tabby's star has been a humbling experience. Before its discovery, the prevailing narrative about stellar photometry was tidy. Dips in brightness are caused by planets, or perhaps by occasional binary companions or eclipsing material. These were well-studied categories. But then came a star that dipped by 22% with no periodicity, no thermal signature, no consistent explanation. Suddenly, the neat categories no longer sufficed. Scientists were reminded that the cosmos often refuses to fit inside our conceptual boxes, and that the practice of science must be flexible enough to accommodate the unexpected. This is one of the core lessons from the unknown. Anomalies are not nuisances to be dismissed, they are golden opportunities. Many of the most profound discoveries in the history of science began with unexplained phenomena. The wobbles in Mercury's orbit led to Einstein's theory of general relativity. The faint glow of cosmic microwave background radiation, once considered a nuisance, became the cornerstone of cosmology. In this tradition, Tabby's star stands as a modern example, a cosmic irregularity that refuses to be ignored, nudging science toward deeper insight. Equally important is the lesson of scientific humility. When the alien megastructure idea first exploded into headlines, it captivated the world. And while most astronomers urged caution, they did not dismiss the public sense of wonder. Instead, they used the opportunity to emphasize a guiding principle: extraordinary claims require extraordinary evidence. Tabby's star reminded scientists and the public alike that skepticism is not cynicism, it is the foundation of rigorous inquiry. At the same time, humility demands openness. To laugh off anomalies as impossible is to close the very doors that lead to discovery. The balance between skepticism and openness is delicate, but essential, and Tabby's star has kept that balance vividly alive. Another powerful lesson is about the evolution of models. Stellar behavior, once thought to be well understood, now must make room for possibilities like long-term dimming trends, transient dust clouds, and complex circumstellar dynamics. If one star can behave this strangely, perhaps others can too. What if the models of stellar life cycles we rely on are missing rare, poorly understood phases? What if the chaotic interplay of debris and dust is more common than we realize? Tabby's star pushes scientists to build more nuanced, flexible models, ones that allow for complexity and rarity. It also underscores the value of patience in science. The mystery of Tabby's star won't be solved overnight, or even in a decade. Some puzzles require generations of observation and theory before clarity emerges. Historical photographic plates hinted at century-long dimming trends. Kepler revealed short-term dips. Modern spectroscopy adds new layers. Only by piecing together datasets across time and technology can we hope to assemble the full picture. This long view is a lesson in perseverance. Science is not always about quick answers, but about relentless curiosity sustained over time. On a cultural level, Tabby's star also teaches us about the power of wonder. The public's fascination with the alien megastructure hypothesis though unlikely, shows that people crave mystery. And rather than dismissing that fascination, scientists can embrace it as a gateway to deeper understanding. Tabby star has drawn people into astronomy who might never have cared about exoplanets or stellar variability. It proves that the unknown has a unique ability to inspire, to spark imaginations, and to remind us that science is not just about cold facts, it's about awe and the thrill of discovery. Perhaps the most profound lesson is this: the unknown is not a problem to be feared, but a gift to be cherished. If the universe offered only phenomena that fit neatly within our existing frameworks, science would stagnate. It is the anomalies, the stars like Tabby, that propel us forward. They challenge us to admit what we don't know, to refine our methods, and to cultivate the humility that is at the heart of genuine exploration. In short, Tabby star is not just an astronomical mystery. It is a teacher. It tells us to stay open-minded, to question assumptions, to refine our models, and to embrace the unknown not as a failure of understanding but as the very frontier of knowledge. The lessons it offers are not limited to astronomy, they extend to all scientific endeavor. Tabby star reminds us that every mystery is an opportunity, every anomaly a doorway, every unanswered question a chance to glimpse the deeper workings of reality. Somewhere in the continuing saga of Tabby's star, one of the most exciting aspects is not just what we already know, or what we don't, but what we might yet discover. The mystery is far from closed, and the future of astronomy holds incredible promise for peeling back the layers of this enigma. While dust is the strongest candidate, there are still too many unanswered questions for scientists to walk away. This is where the power of future observations comes into play. With a new generation of telescopes, both ground-based and space-based, poised to transform our understanding, Tabby star remains firmly on the scientific radar. At the forefront of this effort is the James Webb Space Telescope, JWST. JWST is humanity's most powerful infrared observatory, and infrared is exactly the region of the spectrum that could unlock Tabby's secrets. Remember, one of the puzzles is that while Tabby's star dims dramatically, we don't see the strong infrared glow we'd expect if massive amounts of warm dust were orbiting nearby. JWST has the sensitivity to look for subtle thermal signatures that previous instruments might have missed. If even faint excess infrared radiation is detected, it could confirm the presence of fine dust clouds or disintegrating debris. On the other hand, if JWST finds nothing, no glow at all, that will force astronomers to refine their dust models or consider alternative explanations with even greater care. Beyond infrared, JWST also offers spectroscopic precision that dwarfs anything we've had before. During future dimming events, JWST could break down the starlight into its component wavelengths and detect the unique chemical fingerprints of the material causing the dips. Is it dust-rich in silicates? Is it carbon-based? Could it even be mixed with icy cometary grains? Each chemical signature would tell a story about the origins of the material and whether it comes from circumstellar activity or interstellar clouds drifting past. This level of detail is crucial for moving from broad hypotheses to concrete answers. But JWST is not the only player. Other upcoming facilities promise to contribute. The Vera C. Rubin Observatory, with its ambitious legacy survey of space and time, LSST, will scan the sky continuously over a decade, capturing light curves of billions of stars. This all-sky, long-term monitoring is exactly the kind of dataset needed to see if Tabby's star is truly unique, or if other stars exhibit similar erratic dimming patterns that we've simply overlooked. If LSST finds more Tabby-like stars, we'd know the phenomenon is not unique but part of a larger, rare class of stellar behavior. If none are found, that rarity itself would underscore just how unusual Tabby's star really is. On the ground, next-generation spectrographs are being mounted on some of the largest telescopes on Earth, such as the Extremely Large Telescope, ELT, in Chile. With their massive mirrors and advanced instruments, these observatories could study Tabby's dips in real time with exquisite precision, catching even the smallest wavelength-dependent changes. That means being able to not only confirm the dust hypothesis but also map its distribution, density, and composition in far greater detail than ever before. Additionally, radio telescopes will continue to monitor Tabby's star. Although SETI's earlier searches for alien signals turned up nothing unusual, new instruments like the Square Kilometre Array, SKA, will be far more sensitive, able to detect fainter signals across broader frequency ranges. While aliens remain the least likely explanation, Keeping an ear open costs little, and ensures that if something truly strange were happening, humanity wouldn't miss it. Another avenue is polarimetry, the study of how light is polarized when it passes through dust or gas. Future instruments capable of precise polarimetric measurements could reveal the size, shape, and alignment of the dust grains around Tabby's star. This would be another independent check on the dust hypothesis, providing data beyond brightness dips and spectra. We must also consider the role of time. Continued ground-based monitoring by professional and amateur astronomers alike will remain crucial. Tabby's star's dips are irregular and unpredictable, meaning telescopes must watch it consistently to catch the next major event. The more events recorded, the better scientists can build statistical models, look for hidden periodicities, or test new theories against real data. And because amateur astronomers can contribute valuable observations from small telescopes, Tabby's star will remain one of the best examples of collaborative science bridging the professional and citizen worlds. Finally, future observations won't just be about Tabby's star itself. They'll also be about context. Are there stars like it hiding in the thousands of exoplanetary light curves we already have? Could reanalysis of archival data with modern machine learning tools reveal other candidates? As new surveys collect petabytes of data, AI-driven algorithms will be trained to flag anomalies more systematically than human eyes ever could. Tabby's star was found by volunteers in the Planet Hunters project, but tomorrow, machine learning may find dozens of similar cases, giving astronomers a whole new class of stars to study. So the future of Tabby's star is one of vigilance and curiosity. JWST, Rubin, ELT, SKA, and countless smaller telescopes will continue to probe its light. Each observation is a new piece of the puzzle, narrowing possibilities, discarding dead ends, and sharpening our view of what might be happening. Dust may remain the frontrunner, but if new data uncovers something unexpected, something no current theory fully predicts, then Tabby's star could once again revolutionize how we think about stars, planets, and the chaotic processes around them. In a way, that's the beauty of the situation. Even if dust turns out to be the complete answer, the process of solving the mystery will have advanced astronomy by leaps and bounds. If, however, future telescopes reveal new surprises, then Tabby's star could yet become the key to discovering phenomena we never imagined. Either way, the story is far from over. Somewhere at the end of this extraordinary journey, through dimming light curves, dizzying hypotheses, debates about dust and Dyson spheres, lies a simple truth. Tabby's star is a cosmic reminder that the universe will always outpace our expectations. No matter how sophisticated our theories become, no matter how advanced our instruments grow, there will always be stars, galaxies, and phenomena that defy explanation and humble us into curiosity once more. When astronomers first pointed out the peculiar dips in the brightness of KIC 8462852, they had no idea that it would spark one of the most engaging scientific mysteries of the 21st century. What began as an odd data anomaly blossomed into a worldwide conversation involving professional scientists, citizen astronomers, journalists, podcasters, science fiction fans, and anyone fascinated by the idea that the universe could still surprise us. And that, more than whether the culprit is dust, debris, or something still unimaginable, is the enduring gift of Tabby's star. It's easy to think of science as a process of filling in the blanks, a linear march toward complete understanding. But Tabby's star shows us that science is far richer than that. It is not just about answers, but about questions. Questions that ignite wonder, that challenge assumptions, that force us to refine and stretch our models. The mystery of this star is not a failure to solve the puzzle quickly. It is a testament to the vitality of curiosity. In some sense, the not knowing is as valuable as the knowing. And there's a larger message here, too. In our daily lives, we often seek certainty. We crave neat explanations and tidy narratives. But the cosmos doesn't bend to our desire for simplicity. Instead, it offers complexity, ambiguity, and phenomena that resist resolution. This is not discouragement. It is inspiration. Tabby's star teaches us to embrace uncertainty as part of the scientific adventure, to recognize that the strangest mysteries often carry the seeds of the greatest discoveries. Perhaps, centuries from now, when humanity looks back at the history of astronomy, Tabby's star will be remembered not as the site of an alien megastructure or a unique dust cloud, but as a turning point, a moment when astronomers, confronted with an anomaly, doubled down on open-mindedness, collaboration, and persistence. It may be remembered as a symbol of the way science thrives not on finality, but on endless curiosity. And let's not forget the sheer joy of it. For all the equations and instruments, for all the careful measurements and data modeling, science at its heart is about wonder. Standing under the night sky, pointing a telescope at a distant flickering star nearly 1,500 light-years away, we are reminded that the universe is vast, mysterious, and alive with phenomena we cannot yet explain. That thrill, that spark of awe, is what drives humanity to explore in the first place. So as we leave Tabby's star for now, we do not leave it with closure. We leave it with curiosity, with humility, and with excitement for what lies ahead. Whether the culprit is dust, debris, or something we haven't even conceived of, the lesson remains. The universe is full of surprises, and sometimes the strangest mysteries push science forward. Tabby's star is more than a puzzle. It is an invitation. An invitation to wonder, to question, and to keep looking up, knowing that the next great mystery might already be flickering in the sky, waiting for us to notice. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.